This is the story of how physicists moved faster than light travel from impossible to improbable, and what happened when they discovered that Star Trek had the design right all along. Humanity stands at the edge of something we've dreamed about for generations: travel between stars, reaching distant worlds in weeks instead of millennia, exploring galaxies that currently sit forever beyond our reach. For over a century, one equation kept this dream locked away. Nothing with mass can reach the speed of light, let alone exceed it. Einstein's theory of special relativity seemed ironclad, an absolute cosmic speed limit that physics would never allow us to break. Then in 1994, a young Mexican physicist named Miguel Alcubierre watched an episode of Star Trek and asked himself a simple question: what if the math could actually work? What he discovered didn't break Einstein's rules, but found a loophole so elegant it left physicists stunned. Space itself has no speed limit, which meant you could move a bubble of space faster than light and ride inside it without ever breaking the laws of physics. The spacecraft wouldn't travel through space faster than light. Space would carry the spacecraft, and that difference changed everything. 3 decades later, scientists have refined Alcubierre's vision into something approaching feasibility, reducing energy requirements from the mass of Jupiter to the mass of a small truck. Researchers at NASA's Eagle Works laboratory discovered in 2020 that tiny quantum effects accidentally create nanoscale warp bubbles in laboratory experiments. Teams at Applied Physics published work in 2024 showing that warp drives could function without exotic matter, using only positive energy densities and physics we already understand. Most remarkably, physicist Harold White demonstrated in 2025 that the optimal geometry for a working warp drive matches the twin nacelle design of the USS Enterprise with stunning precision, suggesting that Star Trek's production designers accidentally stumbled onto genuine physical constraints. The breakthroughs keep coming, each one narrowing the gap between theoretical possibility and engineering challenge. Traversable wormholes, once dismissed as mathematical curiosities, showed up in quantum computer simulations in 2022, proving that shortcuts through space-time can exist within known physics. Quantum tunneling experiments revealed that particles can cross barriers in time frames approaching instantaneous, though the implications for faster-than-light travel remain hotly debated. Physicists now openly discuss timelines for warp drive development, comparing the endeavour to multi-generational cathedral construction, rather than dismissing it as fantasy. The universe suddenly seems smaller. Stars that would take tens of thousands of years to reach with conventional propulsion might be accessible within a human lifetime if these technologies mature. Proxima Centauri, our nearest stellar neighbour at 4.2 light-years away, could theoretically be visited and returned from in weeks rather than waiting 40,000 years for a conventional spacecraft to arrive. The implications ripple through every aspect of how we think about humanity's future. None of this comes easy, and the challenges remain staggering. Creating the energy densities required still sits beyond our current capabilities, though the target keeps dropping as models improve. Navigating at warp speed presents problems we're only beginning to understand, from time dilation effects to collision risks with interstellar debris. The Horizon problem threatens to trap spacecraft inside their own warp bubbles, unable to communicate with the outside universe or control their journey. Every solution creates new questions, every breakthrough reveals deeper complexities. But the fundamental shift has already occurred. Faster-than-light travel moved from the realm of fantasy into the category of tremendously difficult engineering problems, which means it's now a question of when rather than if. Universities are teaching courses on warp drive physics, peer-reviewed journals publish regular updates on metric engineering and exotic matter alternatives, and private companies are investing millions in preliminary research. The conversation changed from "can we" to "how do we" when nobody was paying attention, and that transformation marks the real revolution. This story begins with a Friday night in 1994, when Miguel Alcubierre decided to take his love of science fiction seriously. Miguel Alcubierre was pursuing his doctorate in numerical relativity at Cardiff University when he developed the habit of watching Star Trek: The Next Generation with friends every Friday night. The show's premise fascinated him. Captain Picard and his crew travelled between stars at warp speed, covering distances that light would take years to traverse in mere days or weeks. The The technology seemed like pure fantasy, another impossible dream conjured by television writers who cared more about storytelling than physics. Alcubierre couldn't stop thinking about it. As someone who worked daily with Einstein's field equations, the mathematical framework describing how gravity curves space-time, he recognized that the show's writers had tapped into something deeper than they probably realized. General relativity allows space-time itself to expand or contract at any speed, which is why distant galaxies can recede from us faster than light as the universe expands. That expansion doesn't violate Einstein's speed limit, because the galaxies aren't moving through space faster than light. Space itself is carrying them along. The distinction mattered. Special relativity forbids anything with mass from reaching or exceeding light speed when moving through space, but it says nothing about what happens when space itself moves. If you could somehow contract space in front of a spacecraft and expand it behind, you could create a wave of space-time that carries the ship forward. The ship would remain stationary within its local bubble of flat space-time, never experiencing the deadly acceleration that would turn any crew into paste, while the bubble itself surfs across the cosmos at any speed you choose. Einstein's special theory of relativity, published in 1905, revolutionized physics by showing that space and time are intertwined into a four-dimensional fabric called space-time. The theory emerged from Einstein's contemplation of what would happen if you could chase a beam of light at light speed, an impossible thought experiment that revealed deep truths about the universe. Special relativity established that nothing with mass can reach the speed of light, because doing so would require infinite energy, and that time itself slows down for objects moving at high speeds relative to stationary observers. The famous equation relating energy and mass, E equals mc squared, comes directly from special relativity, and shows that mass and energy are equivalent. As an object accelerates toward light speed, its kinetic energy increases without bound, effectively increasing its inertial mass and making further acceleration progressively harder. At 90% of light speed, you need more than twice as much energy to accelerate an object than you did at rest. At 99% of light speed, you need 7 times as much. At 99.9%, over 22 times. The curve approaches infinity as you approach light speed, creating an absolute barrier. General relativity, which Einstein published in 1915, extended these insights to include gravity. Where Newton described gravity as a force acting instantaneously across space, Einstein showed that gravity is the curvature of space-time itself caused by the presence of mass and energy. Massive objects like stars and planets create dimples in the fabric of space-time, and other objects moving through that fabric follow curved paths that we perceive as gravitational attraction. The equations describing this curvature are called the Einstein field equations, and they relate the distribution of matter and energy to the geometry of space-time. These field equations are notoriously difficult to solve. They form a set of 10 coupled nonlinear partial differential equations, meaning they interact with each other in complex ways, and don't have simple solutions for most situations. Physicists have discovered exact solutions for highly symmetric cases, like a perfectly spherical non-rotating star or a rotating black hole, but general solutions require sophisticated numerical methods and powerful computers. Within hours of having this realization, Alcubierre worked out the mathematics. He constructed a metric, a mathematical description of spacetime geometry, that created exactly the effect he imagined. A bubble of flat spacetime surrounded by a region where space contracts ahead and expands behind. The math was consistent with Einstein's field equations, meaning it didn't violate general relativity. The solution was elegant, almost beautiful in its simplicity, and it suggested that warp drives weren't just science fiction after all. The Alcubierre metric describes space-time using 4 coordinates, time and 3 spatial dimensions. In normal flat space-time far from any massive objects, the metric has a simple form called the Minkowski metric, which describes how distances and time intervals relate to each other. Alcubierre's modification introduces a velocity field that varies with position, creating regions where spacetime contracts or expands depending on where you are relative to the spacecraft. The key insight involves the shift vector, a mathematical object that describes how space flows in time. In normal physics, space doesn't flow, it just sits there while objects move through it. But general relativity allows space itself to have motion, and the Alcubierre metric exploits this by creating a shift vector that varies dramatically near the warp bubble. The shift vector pulls space forward in front of the bubble and pushes it backward behind, creating the warp effect. Mathematically, the metric includes a shape function that determines how sharply the warp field transitions from contracted space ahead to expanded space behind. This shape function can be adjusted to control the bubble's properties, trading off between different desirable characteristics. A sharper transition concentrates the warp effect into a smaller volume, but requires more extreme space-time curvature. A gentler transition spreads the effect over a larger region but may make the bubble harder to control. The thickness of the warp bubble's wall, the region where space transitions from contracted to expanded, plays a critical role in determining energy requirements. Alcubierre's original calculations used a relatively thin wall, which created intense curvature gradients and consequently enormous energy demands. Later researchers discovered that thickening the wall, spreading the transition over a larger distance, could reduce energy requirements significantly, while maintaining the same transport effect. The paper Alcubierre published in '94 hit the physics community like a thunderbolt. Here was a serious researcher, working within established theoretical frameworks, presenting a mathematically sound model for faster-than-light travel. The journal Classical and Quantum Gravity accepted his work after peer review, lending it the credibility that separates legitimate physics from speculation. Physicists who had dismissed warp drives as impossible suddenly had to confront the possibility that they might be theoretically achievable. But Alcubierre's paper also revealed why building such a device remained firmly in the realm of fantasy. His calculations showed that creating even a modest warp bubble, perhaps 10 meters across, would require energy equivalent to the mass of Jupiter converted entirely into the exotic form needed to sustain the bubble. Jupiter has a mass about 300 times that of Earth, containing roughly 1.9 times 10 to the 27th power kilograms of matter. Converting all of that into pure energy, and then somehow transforming that energy into the specific type needed for the warp drive, represented a feat so far beyond current capabilities that it might as well be magic. The energy calculation starts with Einstein's famous equation relating mass and energy. 1 kilogram of matter completely converted to energy yields roughly 9 times 10 to the 16th power joules, enough to power the entire United States for about 3 days. Jupiter's mass would yield about 1.7 times 10 to the 44th power joules when fully converted, roughly equivalent to the total energy output of the Sun over 100 million years. That number is so large it defies intuitive understanding. To put it in more tangible terms, imagine every power plant on Earth operating continuously for trillions of years. You still wouldn't generate enough energy. The entire human civilization's energy consumption throughout history, from the first fires our ancestors lit to every nuclear reactor currently operating, amounts to perhaps 10 to the 21st power joules, a trillion times less than what Alcubierre's original calculations required. Even if we could somehow harness the Sun's total output, capturing every photon it emits, we'd need to do so for longer than the current age of the universe to accumulate sufficient energy. Worse still, the energy had to be negative. Not just ordinary energy in reverse, but something called negative energy density, a theoretical concept that violates what physicists call energy conditions. In normal physics, energy density is always positive or zero, never negative. When you have matter or radiation in a region of space, it increases the energy density there. Empty space, even complete vacuum, has a baseline energy density that quantum mechanics predicts should be positive, though extraordinarily small. Negative energy density would mean having less energy in a region than empty space contains, creating a deficit that pulls space-time in unusual ways. Normal positive energy density curves space-time in a manner we recognize as gravity, pulling things together. Negative energy density would curve space-time in the opposite sense, pushing things apart, creating gravitational repulsion rather than attraction. This exotic property is exactly what's needed to make the warp bubble work, allowing space to expand behind the craft rather than contracting everywhere as normal gravity would dictate. Quantum mechanics hints that negative energy might exist in certain circumstances. The Heisenberg uncertainty principle, one of the foundational results of quantum mechanics, states that you can never simultaneously know certain pairs of properties with perfect precision. For energy and time, The uncertainty principle implies that over very short time intervals, energy can fluctuate wildly, including potentially becoming negative briefly before returning to positive values. These quantum fluctuations are real and measurable. They cause observable effects like the Lamb shift in atomic spectra and contribute to the Casimir force between nearby metal plates. Virtual particles constantly pop into and out of existence everywhere in space, borrowing energy from the vacuum for infinitesimally short periods, before annihilating and returning that energy. These processes are carefully balanced so that on average, the energy density remains positive, but there are fleeting moments and tiny regions where the energy density dips below zero. The challenge is capturing and concentrating these fleeting negative energy fluctuations to create macroscopic amounts that could sustain a warp bubble. Quantum field theory imposes strict constraints called quantum inequalities that limit how much negative energy can accumulate in any given region and for how long. You might be able to create a pulse of significant negative energy lasting nanoseconds in a region the size of an atom, but scaling that up to cubic meters and seconds or longer may be fundamentally impossible according to current understanding. Alcubierre's warp drive needed not just a little bit, but enough to fill a bubble tens of meters across, maintaining it indefinitely against the tendency of spacetime to smooth out such extreme distortions. The quantum inequalities suggest this might require violating fundamental laws of quantum field theory, potentially making the whole concept impossible regardless of how much ordinary energy you could provide. The stress-energy tensor, the mathematical object that describes matter and energy distribution in Einstein's equations, takes on bizarre properties for the Alcubierre metric. In normal physics, the stress-energy tensor has components representing energy density, momentum density, and pressure, all of which must satisfy certain relationships to be physically reasonable. For ordinary matter, energy density is positive, pressure is positive or negative within certain bounds, and energy flows slower than light. For the Alcubierre drive, the stress-energy tensor violates multiple energy conditions simultaneously. The weak energy condition, which requires that energy density be positive for all observers, is violated because you need negative energy density. The null energy condition, which constrains how energy can flow along light-like paths, is violated because the warp bubble structure requires energy to flow in ways forbidden by this condition. The strong and dominant energy conditions, which impose additional constraints on pressure and energy density, are also violated. The mechanism itself was straightforward once you accepted these impossible requirements. The warp bubble surrounds a central region of flat spacetime where the spacecraft sits. Outside this region, space contracts in front at a rate determined by how fast you want to go, while expanding behind at the same rate. The spacecraft doesn't move within its local bubble, so from the crew's perspective they experience no acceleration, no g-forces, nothing but smooth riding as if they were sitting still. Time inside the bubble flows normally, synchronized with the outside universe, so the crew doesn't experience time dilation or arrive at their destination centuries in the future relative to everyone they left behind. From an external observer's viewpoint, the bubble itself moves across space, potentially at many times the speed of light. A ship travelling from Earth to Proxima Centauri at 10 times light speed would make the journey in about 5 months, compared to the 4.2 years it takes light to cover that distance conventionally. Increase the warp speed to 100 times light, and the journey drops to 2 weeks. The only limit is how much energy you can pump into warping spacetime, and even that limit is theoretical since Einstein's equations don't forbid arbitrarily large distortions. Scientists immediately began picking apart Alcubierre's work, looking for flaws or hidden problems. Some pointed out that the field equations didn't specify how to create such a warp bubble in the first place, only that one could exist if you somehow managed to arrange the right energy distribution. Others noted that the bubble might be unstable, collapsing as soon as it formed unless maintained by continuous energy input. The horizon problem emerged quickly. The interior of the warp bubble becomes causally disconnected from the exterior, meaning an astronaut inside couldn't send signals to control the bubble's speed or direction, since those signals couldn't escape to reach the bubble's edge. Time travel paradoxes raise deeper concerns. General relativity links space and time inextricably, so anything that lets you manipulate space to achieve faster than light travel potentially opens the door to travelling backward in time. If you could create 2 warp bubbles and arrange their trajectories correctly, you might be able to set up a closed time-like curve, a path through space-time that loops back to its own past. This would create all the classic time travel paradoxes. Could you kill your grandfather before he met your grandmother? Could you prevent your own birth? Would the universe simply forbid such configurations? Physicists split on how to interpret these problems. Some argued that any theory allowing faster-than-light travel automatically allows time travel. So if we believe time travel is impossible, then faster-than-light travel must also be impossible. Others suggested that quantum effects not included in Alcubierre's classical calculations would prevent time travel paradoxes, perhaps by destroying warp bubbles before they could be arranged into problematic configurations. Still others embraced the possibility of time travel, arguing that consistency conditions or parallel universes might resolve the paradoxes without making the physics impossible. Despite these complications, Alcubierre's work permanently changed how physicists thought about interstellar travel. The speed of light was no longer an absolute barrier, but rather a limit on how fast things can move through space. If you could move space itself, you could sidestep that limit entirely. The question shifted from can we ever reach other stars to can we engineer the conditions Alcubierre's equations require, a transformation that moved the problem from fundamental physics to engineering, even if that engineering remained centuries beyond current capabilities. Alcubierre himself was modest about the implications, later saying he never expected his idea to be practical. He returned to his primary research on black holes and numerical relativity, content to have shown that the mathematics worked even if the physics remained impossible. But he had opened a door that others would spend decades trying to widen, looking for ways to make the requirements less absurd, the energy demands smaller, the exotic matter less exotic. The next major step came from an unlikely place, NASA's Johnson Space Center in Houston, where an aerospace engineer was about to become obsessed with turning science fiction into reality. Harold Sonny White grew up in Washington, D.C., wandering the halls of the Smithsonian Air and Space Museum, absorbing every exhibit about rockets and spacecraft and the dream of human expansion beyond Earth. That childhood fascination turned into a career when he joined Boeing in the late 1990s as an engineer working on advanced aerospace concepts. While pursuing a master's degree in physics at the same time, White encountered Alcubierre's 1994 paper and found himself captivated by the possibility that warp drives might actually work. The timing was perfect. White was learning the mathematical tools needed to work in general relativity, studying the field equations that describe how matter and energy curve space-time. Alcubierre's metric provided a concrete example to analyze, and White quickly realized that the original calculations left room for optimization. The specific shape of the warp bubble, the thickness of the region where space contracted and expanded, the geometry of how energy distributed itself around the spacecraft, all of these factors could potentially be adjusted to reduce the energy requirements from impossibly large to merely incredibly large. White's background in engineering gave him a different perspective than most theoretical physicists. Where pure theorists focused on whether something was possible in principle, White thought about what it would take to actually build a working device. He asked practical questions. How would you contain the exotic matter? How would you control the bubble's geometry? What materials could withstand the stresses? How would the crew survive inside the bubble? These engineering concerns led him to explore different mathematical configurations that might be more buildable even if they required slightly more energy. The gap between theoretical physics and practical engineering is often vast. Physicists might prove that some phenomenon is possible according to the laws of nature, but that doesn't mean engineers can build devices exploiting that phenomenon. Superconductors work beautifully in theory, and even in laboratory demonstrations, yet we still don't have room temperature superconductors despite decades of research. Fusion power has been 20 years away for the past 60 years, because the engineering challenges of containing 100 million degree plasma are extraordinarily difficult even though the underlying physics is well understood. After completing his PhD in physics at Rice University, White joined NASA in 2004 as an expert in advanced propulsion concepts. The agency was beginning to think seriously about what technologies might enable interstellar missions in the coming centuries, and White's unique combination of engineering experience and theoretical physics knowledge made him valuable for evaluating radical ideas. By 2011, he had become the head of NASA's EagleWorks laboratory, a small research group at Johnson Space Center dedicated to studying physics that might one day revolutionize space travel. Eagleworks operated on a shoestring budget by NASA standards, perhaps a few $100,000 per year compared to billions for flagship missions. The lab's mandate was to investigate long-shot ideas that might not pay off for decades or centuries, but could transform human capabilities if they worked. Warp drives fit perfectly into this category, along with other speculative propulsion concepts like quantum vacuum thrusters and electromagnetic drives that claim to generate thrust without expelling reaction mass. White's first major contribution came in 2012 when he published a paper titled Warp Field Mechanics 101 that refined Alcubierre's original calculations. Working with the physicist Richard Obusi, White showed that changing the warp bubble from a simple spherical shell to a toroidal or donut shape, more like Saturn's rings than a soap bubble, could dramatically reduce energy requirements. The oscillating intensity of the energy field, pulsing rather than remaining constant, lowered demands even further. White's calculations suggested that a warp bubble about 10 meters in diameter might need energy equivalent to only 700 kilograms of matter, converted to the right form. The toroidal geometry works by concentrating the warp effect into a smaller total volume of space-time. Instead of warping space uniformly in all directions around the spacecraft, you focus the warping into a ring surrounding the ship. The interior of the ring maintains flat space-time where the crew resides safely, while the ring itself does all the work of contracting space ahead and expanding it behind. This concentration means you're warping less total volume, which directly reduces the energy needed. Oscillating the field intensity adds another layer of optimization. Rather than maintaining constant negative energy throughout the warp bubble's operation, you pulse the field on and off rapidly, perhaps millions or billions of times per second. During the brief moments when the field is on, you need intense negative energy, but you only need to sustain it for fractions of a microsecond before switching off. The time-averaged negative energy becomes much smaller than what steady-state operation would require. This oscillation trick exploits quantum mechanics in clever ways. The quantum inequalities that limit negative energy accumulation impose constraints that depend on how long the negative energy persists. Brief pulses can achieve larger negative energy densities than sustained fields, even though the time-averaged amount remains modest. By pulsing rapidly, you might be able to create the instantaneous conditions needed for warp bubble formation while respecting the quantum limits on time-averaged negative energy. 700 kilograms is still enormous by any practical standard, representing roughly as much mass as a small car completely annihilated and transformed into exotic energy. But compared to Jupiter's mass, it represented a reduction of about 25 orders of magnitude, dropping the requirement from 10 to the 27th power kilograms to 10 to the 3rd power. That kind of improvement, achieved purely through mathematical optimization without any new physics, suggested that further refinements might make the requirements smaller still. White didn't stop at theoretical calculations. Working with NASA engineers and outside collaborators, he designed and built the White-Jude Warp Field Interferometer, a device intended to detect microscopic distortions in space-time that might indicate the presence of a tiny warp bubble. The interferometer used laser beams to measure tiny changes in the path-length light traveled through a carefully controlled cavity, looking for the signature pattern that would appear if space-time was being weakly warped in the expected way. The interferometer worked by splitting a laser beam into two paths that traveled through slightly different regions of space before recombining. If one path experienced even a tiny warp field while the other didn't, the two beams would be slightly out of phase when they recombined, creating an interference pattern that the detector could measure. The device could detect path length changes smaller than the width of an atomic nucleus, making it sensitive enough to potentially observe the minuscule warp effects that might be created in laboratory conditions. The setup required extraordinary stability and isolation from vibrations. Earthquakes, passing trucks, even people walking in nearby hallways could create disturbances larger than the signal they were trying to detect. The team mounted the interferometer on vibration isolation platforms, enclosed it in vacuum chambers to eliminate air currents, and carefully controlled the temperature to prevent thermal expansion from creating false signals. Despite these precautions, distinguishing genuine warp field effects from instrumental artifacts remained incredibly challenging. The experiments didn't produce conclusive evidence of actual warp bubbles, but they pushed the boundaries of what could be measured and demonstrated that NASA was willing to take the concept seriously enough to fund real laboratory work. White and his team conducted presentations at aerospace conferences, published in peer-reviewed journals, and gradually built a community of researchers willing to work on what had previously been dismissed as fringe science. Critics within NASA and the broader physics community questioned whether EagleWorks was wasting resources on impossible physics. Some argued that proving warp drives were impossible would be more valuable than pursuing them based on speculative calculations that might contain subtle errors. Others worried that association with such far-out concepts would damage NASA's reputation for serious scientific work. White defended the research by pointing out that small investments in high-risk, high-reward concepts had historical precedent in aerospace development, and that completely dismissing radical ideas without investigation was bad scientific practice. By 2013, White was collaborating with artists and engineers to visualize what a warp-capable spacecraft might actually look like. The result, the USS Enterprise, named in homage to Star Trek but officially standing for Interstellar Experimental Ship, featured the twin nacelle design that White's math suggested would be optimal. Long cylindrical structures extending from a central hull housed the exotic energy, positioned far enough from the crew compartment to minimize any harmful effects while maintaining the warp bubble geometry. The design wasn't just artistic license. White's calculations showed that the nacelles needed to be separated from the main hull by a certain distance to create the right stress-energy distribution, and that distance happened to match the proportions that the Star Trek designers had chosen decades earlier, based purely on aesthetic considerations. This convergence between physics and fiction delighted fans and gave researchers confidence that they were on the right track, even if the actual construction remained far beyond current capabilities. White emphasized repeatedly that his work represented theoretical exploration, not engineering ready for implementation. The 700-kilogram mass energy requirement, while vastly smaller than Alcubierre's original calculation, still required technology that doesn't exist and might not be possible. Creating negative energy in macroscopic quantities remained purely hypothetical, relying on quantum effects that had never been observed at the scales needed. The stability problems, the horizon issue, the time travel paradoxes, all of the difficulties that plagued Alcubierre's original concept still applied to the optimized version. But White's contributions moved the conversation forward. He showed that systematic optimization could reduce impossible requirements to merely incredibly difficult ones, and that pattern suggested further progress might be possible. His willingness to work openly on the problem, publishing in mainstream journals and presenting at scientific conferences, rather than hiding behind classification or staying in the shadows of fringe research, gave other physicists permission to take warp drives seriously. The field was evolving from a single groundbreaking paper into a research program, with multiple teams working on different aspects of the problem. Some focused on reducing energy requirements further, others on understanding stability and control issues, still others on exploring alternative geometries that might achieve similar effects with different trade-offs. White's work at NASA became a catalyst for this broader exploration, demonstrating that serious scientists could study warp drives without sacrificing their credibility. Then, in 2020, while conducting experiments for an entirely different purpose, White noticed something that would prove far more significant than any of his previous work. In late 2020, Harold White's laboratory at the Limitless Space Institute was conducting research funded by the Defense Advanced Research Projects Agency, looking at ways to harvest energy from quantum vacuum fluctuations. The team was studying Casimir cavities, microscopic spaces between precisely positioned metal plates where quantum effects create measurable forces. The experiments had nothing to do with warp drives. White and his colleagues were exploring whether they could extract usable energy from what physicists call the quantum vacuum. Quantum mechanics teaches that empty space isn't truly empty. Even in a perfect vacuum, with every particle removed and the temperature lowered to absolute zero, the universe refuses to sit still. Virtual particles constantly flicker in and out of existence, borrowing energy from the vacuum for infinitesimally brief moments before annihilating and returning that energy. These quantum fluctuations are real, measurable, and have observable effects on how particles behave. The vacuum energy arises from the Heisenberg uncertainty principle applied to electromagnetic fields. Just as you cannot simultaneously know a particle's position and momentum with perfect precision, you cannot simultaneously know the strength of an electromagnetic field and how rapidly it's changing. This uncertainty means that even in vacuum, electromagnetic fields must fluctuate, never settling to exactly zero. These fluctuations manifest as virtual photons appearing and disappearing throughout space. Virtual particles are not the same as real particles. They exist only briefly, their energy and momentum constrained by the uncertainty principle to values that would violate energy conservation if sustained indefinitely. A virtual photon might carry tremendous energy, but it must disappear within a time interval so short that the energy-time uncertainty principle permits the violation. These fleeting existences add up to create measurable effects. The most famous is the Lamb shift, discovered in 1947 by Willis Lamb while studying hydrogen atoms. The energy levels of electrons in hydrogen atoms are very slightly different from what Dirac's equation predicts, with the discrepancy explained by interactions with virtual photons from the vacuum. The electrons constantly emit and reabsorb virtual photons, and this process alters their effective mass and charge in subtle but measurable ways. Dutch physicist Hendrik Casimir predicted in 1948 that if you place two uncharged metal plates extremely close together in a vacuum, the quantum fluctuations between the plates would be restricted compared to the fluctuations outside. Only certain wavelengths of virtual particles can fit in the narrow gap, while all wavelengths are available in the open space beyond. This difference in quantum fluctuation density creates a net force, pushing the plates together, as if trying to eliminate the gap. Casimir's calculations showed that the force per unit area between parallel plates separated by distance d is proportional to 1/d to the fourth power, meaning the force drops off rapidly as you separate the plates but becomes enormous at very small separations. For plates 1 micrometer apart, about 1/100th the width of a human hair, the force amounts to about 1/100th of a Newton per square meter. That sounds tiny, but at the microscale it's significant, equivalent to the weight of a small insect pressing on an area the size of your fingernail. The effect is incredibly weak. For plates separated by 1 micrometer, roughly 1/100th the width of a human hair, the force amounts to only about 1/10,000th of a Newton per square meter. To put that in perspective, atmospheric pressure at sea level is about 100,000 newtons per square meter, meaning the Casimir force is about 1 billion times weaker than the air pushing on your body right now. You need incredibly sensitive equipment to measure it, which is why the effect wasn't confirmed experimentally until 1997, nearly 50 years after Casimir's prediction. The experimental challenges were formidable. Measuring forces that's small requires eliminating every other source of noise and disturbance. Thermal fluctuations, electromagnetic interference, vibrations from the building or passing vehicles, air currents, even the gravitational effects of people moving nearby can create signals larger than the Casimir force. Early attempts to measure the effect produced conflicting results because researchers couldn't adequately control all these confounding factors. Stephen Lamoureux, working at the University of Washington, built an apparatus that could detect forces as small as 1 part in 10,000 billion of a Newton. His experiments conclusively demonstrated that the Casimir force exists and matches theoretical predictions. The measurements also verified that the region between the plates contains less energy than the vacuum outside, creating what physicists call negative energy density. Not negative in the sense of being antimatter or having negative mass, but negative relative to the baseline energy of empty space. Lamoureux's apparatus used a torsion pendulum, essentially a metal plate suspended by a thin quartz fibre that could twist in response to tiny forces. He brought a metal sphere close to the plate and measured how the fibre twisted as the sphere approached. By carefully calibrating the system and measuring the force at different separations, he could extract the Casimir force from all the other effects present. His measurements matched Casimir's predictions to within 15%, well within the experimental uncertainties. This matters for warp drives because Alcubierre's equations require exactly this kind of negative energy density to create the space-time distortion needed for faster-than-light travel. Physicists had long suspected that quantum effects might provide the exotic matter the equations demanded, but the amount seemed impossibly small. Lamoureux's measurements showed negative energy densities of about 10 to the negative 4th power joules per cubic meter, which is 100,000 billion times lighter than the energy density of a kilogram of matter in a cubic meter of space. To understand just how inadequate these quantities are, consider that Alcubierre's original warp drive required negative energy densities of perhaps 10 to the 20th power joules per cubic meter, 24 orders of magnitude larger than what the Casimir effect produces naturally. Scaling up from laboratory-scale Casimir cavities to spacecraft-scale warp bubbles while maintaining sufficient negative energy density represents a challenge of truly staggering proportions. The negative energy density in Casimir cavities arises because quantum field theory assigns an energy to every mode of the electromagnetic field. In free space, all possible wavelengths contribute to the vacuum energy. Between closely spaced plates, only wavelengths that fit between the plates can contribute, which excludes most of the modes. Subtracting the energy density between the plates from the energy density outside yields a negative difference, even though both quantities are actually positive when measured against absolute zero energy. This subtlety matters because it means Casimir cavities don't actually contain exotic matter in the sense of stuff with inherent negative mass or energy. They're just regions where the quantum vacuum has slightly less energy than neighbouring regions. The negative energy is relative, not absolute. Whether this distinction matters for warp drives depends on subtle details of how you formulate the physics, and different researchers have different opinions about whether relative negative energy suffices or whether absolute negative energy is required. White's 2020 experiments were examining how the Casimir effect behaved in more complex geometries than simple parallel plates. His team created microscopic structures with cylindrical cavities and measured the energy distribution using advanced imaging techniques. When they analysed the data, White noticed a pattern in how the negative energy distributed itself around the tiny cylindrical columns they had placed between the plates. The pattern was familiar. White had spent years studying the energy distributions required for Alcubierre warp bubbles, and he recognised immediately that the quantum vacuum energy between the plates matched almost exactly the signature of negative energy that a warp bubble would create. The scales were wildly different, nanometers versus meters, but the geometry was identical. The mathematical similarity was striking. Both warp bubbles and Casimir cavities exhibit negative energy density concentrated in specific regions with particular geometric patterns. Both require careful shaping of the energy distribution to achieve the desired effect, whether that's warping spacetime or generating an attractive force. Both satisfy the same differential equations describing how energy and spacetime geometry relate. White and his colleagues ran calculations to see what would happen if they optimized the structure. They modeled a 1-micron sphere, about 1/100th the width of a human hair surrounded by a 4-micron cylindrical cavity. The math showed that this structure could generate a nanoscale warp bubble, encapsulating the central sphere. The bubble would be far too small to transport anything macroscopic, and its distortion of spacetime would be barely measurable, but it represented the first physically realizable structure that could create a genuine warp field using known physics. The discovery didn't mean White had built a working warp drive or even demonstrated that such a thing was possible at useful scales. What he found was that the quantum vacuum naturally creates the right type of energy distribution in the right geometric configuration to produce a warp bubble, even if only at scales trillions of times smaller than would be needed for spacecraft. The negative energy existed, could be created without exotic matter, and arranged itself in the correct pattern purely through quantum mechanical effects. This mattered because it proved that warp bubbles aren't purely mathematical abstractions requiring impossible physics. They emerge naturally from quantum mechanics, even if only at microscopic scales. If nature can create warp bubbles spontaneously through quantum effects, then perhaps we can engineer ways to amplify those effects to macroscopic scales. The gap between what's theoretically possible and what's practically achievable narrowed significantly. White's team published their results in the European Physics Journal, describing the Casimir cavity geometry that produced the warp bubble signature. The paper sparked intense debate among physicists. Some argued that calling these quantum fluctuations a warp bubble overstated what was actually happening, that the mathematical similarity didn't mean you could scale up the effect. Others pointed out that the discovery validated the basic concept, showing that spacetime distortions with the right properties can and do occur in nature. The Casimir effect itself offered a potential path toward generating the exotic energy a full-scale warp drive would need. If quantum vacuum fluctuations between plates naturally create negative energy density, then perhaps carefully designed metamaterials with microscopic structures could amplify this effect. You would need trillions of tiny cavities, each contributing a minute amount of negative energy, all arranged to focus their combined effect into a macroscopic warp bubble. Researchers began exploring whether such amplification was theoretically possible. The quantum vacuum has natural limits. You can't extract arbitrary amounts of negative energy, because quantum field theory imposes constraints called quantum inequalities that limit how much negative energy can accumulate in any given region. These inequalities suggest that while you can create temporary pulses of significant negative energy density, maintaining it indefinitely over large volumes might be prohibited by fundamental physics. Still, the discovery opened new avenues for research. Instead of assuming that exotic matter with negative energy must somehow exist but remains undiscovered, physicists could now study how quantum vacuum effects scale and whether there are clever ways to concentrate or amplify them. The problem shifted from where do we find negative energy to how do we make more of this negative energy we've already found, a much more tractable engineering challenge even if still enormously difficult. White's work at the Limitless Space Institute continued, exploring whether the Casimir effect could be harnessed not just for warp drives, but for more immediate applications like power generation. The amount of energy extractable from quantum vacuum fluctuations is tiny, measured in microwatts for structures the size of computer chips. But for certain applications like remote sensors or medical implants, tiny amounts of continuous power could be valuable. The connection between Casimir cavities and warp bubbles remained the most exciting result. White had shown that if you place a microscopic sphere in just the right cylindrical cavity, the quantum vacuum arranges itself to create a genuine warp field, distorting space-time in exactly the way Alcubierre's equations describe. Scale that up by a factor of 1 billion, and you'd have a warp drive. The challenge, of course, is that scaling up by 1 billion might not be possible, given the constraints quantum field theory imposes. While White was discovering these quantum connections, other researchers were pursuing a different approach, eliminating the need for negative energy entirely. In May 2024, a team at the Advanced Propulsion Laboratory of Applied Physics published a paper in the journal Classical and Quantum Gravity that sent shockwaves through the warp drive research community. Jared Fuchs from the University of Alabama in Huntsville and Christopher Helmerich had achieved something physicists thought impossible. They designed a warp bubble that satisfied all 4 major energy conditions using only positive energy densities, completely eliminating the need for exotic matter. Energy conditions in general relativity are mathematical statements about what kinds of matter and energy can exist in our universe. The weak energy condition says that energy density must be non-negative as measured by any observer. The null energy condition says that energy can't flow faster than light. The strong energy condition requires that energy density plus pressure must be non-negative in all directions. The dominant energy condition combines these, demanding that energy density exceeds pressure magnitude while also flowing slower than light. Alcubierre's original warp drive violates all 4 of these conditions, requiring negative energy density and bizarre pressure distributions that don't correspond to any known form of matter. White's optimizations reduced the amount of negative energy needed but didn't eliminate it. Fuchs and Helmerich took a completely different approach. Instead of trying to minimize the violation of energy conditions, they redesigned the warp bubble geometry to satisfy the conditions entirely. The key insight involved accepting a significant constraint. Their warp drive was subliminal, limited to speeds below that of light. This sounds like a defeat until you consider that even travelling at 10% of light speed would be revolutionary for space exploration. At 1/10 light speed, you could reach Proxima Centauri in 42 years instead of the tens of thousands of years required with conventional propulsion. Mars could be reached in about 4 minutes instead of months. By restricting themselves to subliminal speeds, Fuchs and Helmerich could construct warp bubbles using positive energy densities that don't violate any energy conditions. The space-time distortion still exists, space still contracts in front and expands behind, but the magnitude of the distortion remains within bounds that known physics allows. You're not breaking causality or requiring exotic matter, you're just cleverly arranging ordinary mass energy to create a useful effect. The energy requirements remained astronomical. Their calculations showed that creating a warp bubble, 10 meters in diameter, travelling at even a fraction of light speed, would require mass energy equivalent to several Jupiter masses concentrated into a carefully designed shell. This didn't make the drive practically buildable, but it represented a major conceptual advance. Warp drives are possible using physics we actually understand, without invoking speculative quantum effects or undiscovered forms of matter. Fuchs and Helmerich developed their work using a publicly available online toolkit called Warp Factory, software they created that allows researchers to test different warp drive geometries and check whether they violate energy conditions or other physical constraints. The tool automates the tedious calculations required to verify whether a given spacetime metric is physically reasonable, democratizing warp drive research by making it accessible to anyone with the mathematical background to use it. Applied Physics, a non-profit organization dedicated to advancing breakthrough propulsion research, supported the work through its Warp Grant program. The organization's CEO, Yanni Martyr, had been collaborating since 2021 with astrophysicist Alexei Bobrik on a theoretical framework for what they called physical warp drives, distinguishing them from the purely mathematical constructs that violate energy conditions. Their work showed that an entire class of subliminal warp drive spacetimes could be constructed using positive energy densities, not just one specific solution. The Bobrik-Martyr framework, published in Classical and Quantum Gravity in 2021, provided the theoretical foundation that Fuchs and Helmerich built upon. It demonstrated that the mathematical structure of general relativity allows for warp-like transport of objects at high speeds using only matter that satisfies energy conditions. The catch is that you need absurdly large amounts of this matter, concentrated in specific geometric configurations, and you need to accelerate it in precisely controlled ways. Think of it as the difference between levitating a person through anti-gravity, which requires exotic physics we don't have, versus lifting them with a forklift, which requires enormous machinery and careful engineering but no new physics. The Bobrik-Martyr approach and its refinements by Fuchs and Helmerich trade exotic matter for engineering challenges. You can build a warp drive with known physics, but you need technology that makes our current capabilities look like Stone Age tools. The subliminal warp drive also avoided several nasty problems that plague faster-than-light versions. Time travel paradoxes disappear because you're not violating causality. The horizon problem becomes less severe because information can still propagate across the warp bubble at light speed, giving you some ability to control the bubble from within. Stability issues may be more manageable when you're not pushing spacetime to extreme distortions. Critics pointed out that calling something a warp drive when it can't exceed light speed seems misleading, since the whole point of warp drive is to enable faster-than-light travel. Proponents argued that establishing feasibility at subliminal speeds represents crucial progress, proving that the basic concept works before trying to push it to superluminal regimes. If you can build a working subliminal warp drive, you've demonstrated that controlled spacetime distortion is possible, which makes further improvements more plausible. Miguel Alcubierre himself endorsed the work, noting that showing warp drives can exist within known physics without requiring negative energy was a significant achievement even if it didn't solve all the problems. The fact that the original proposer of warp drive theory validated this new direction gave the research additional credibility and encouraged other physicists to take the positive energy approach seriously. The subliminal warp drive also created a clear research roadmap. Engineers could work on the materials science needed to create ultra-dense matter distributions, the control systems required to precisely shape warp bubbles, the power generation that could produce the necessary energy, all without waiting for breakthroughs in exotic matter physics. The problem became one of advancing technology, rather than hoping for discoveries in fundamental physics. Applied Physics expanded its grant program, funding additional researchers to explore related questions. How small could you make a warp bubble and still have it be useful? Could you create microscopic warp drives that transport individual atoms or molecules? Might warp effects have applications beyond spacecraft propulsion, perhaps in manufacturing or scientific instrumentation? Each question opened new avenues for investigation. The organization also began public outreach, explaining to non-specialist audiences how warp drives had moved from impossible to theoretically possible, trying to generate interest and funding for what would necessarily be a long-term research program. Martyr compared the effort to medieval cathedral construction, where builders knew they wouldn't live to see completion but worked anyway, contributing to a project that would benefit future generations. Meanwhile, Harold White was making another discovery that would bring the conversation full circle back to Star Trek. In 2025, Harold White published a paper with his colleagues at Casimir Space that analysed warp bubble geometries in unprecedented detail, focusing on what happens when you break the continuous energy ring that Alcubierre envisioned into discrete cylindrical sections. The math had been evolving toward this for years, but White's new work made the connection explicit. The optimal configuration for a warp drive, balancing energy efficiency against crew safety and control, involves twin cylindrical nacelles positioned on either side of a central habitable zone. It was the USS Enterprise, Gene Roddenberry's designers, working in the 1960s with no knowledge of general relativity or warp drive physics, had accidentally landed on a configuration that genuine physics now suggested was close to ideal. The paper, titled Interior Flat Cylindrical Nacelle Warp Bubbles, Derivation and Comparison with Alcubierre Model, showed how splitting the warp field into separate engine pods solved several problems simultaneously. The interior of each nacelle could remain flat and safe while containing the exotic energy needed to create the warp effect. The separation between nacelles and the main hull kept dangerous energy gradients away from the crew. The modular architecture allowed independent control of each nacelle, providing redundancy and better handling characteristics. White told reporters that the resemblance to Star Trek's most famous spacecraft wasn't merely aesthetic but reflected a potential convergence between physical requirements and engineering design, where science fiction architectures hint at practical pathways for real, warp-capable configurations. In other words, when you work out the physics rigorously, you end up at the same place the TV show's artist reached through intuition and visual appeal. The explanation involves understanding how warp bubbles distort space-time and what that distortion does to anything inside. Alcubierre's original spherical bubble creates a uniform distortion field surrounding the spacecraft, which seems elegant but creates problems. The energy density required to maintain the bubble concentrates at the bubble's edge, forming a shell where space-time is violently curved. Any matter that passes through this shell experiences enormous tidal forces as the space-time curvature changes rapidly. If your spacecraft is centered perfectly in the bubble, you're protected because you're surrounded by the uniform flat region inside. But any deviation from center, any wobble or drift, brings you dangerously close to the edge where the forces would tear the ship apart. You need incredibly precise positioning and stability, which becomes harder to maintain as the bubble moves and interacts with the matter and energy it encounters along the way. Breaking the warp field into cylindrical nacelles changes the geometry fundamentally. Instead of one continuous shell, you have two separate regions of strong space-time curvature, positioned away from the central spacecraft. The interior of each nacelle houses the exotic energy source, but the energy is contained and controlled within the nacelle structure. The central region where the crew lives experiences flat space-time, completely shielded from the dangerous curvature regions by the geometric arrangement. This configuration also solves a timing problem. For a warp bubble to work correctly, the contraction of space in front must synchronize with the expansion behind. If the timing slips, the bubble destabilizes and collapses. In a continuous spherical shell, maintaining this synchronization requires perfect coordination around the entire bubble. With two discrete nacelles, you can independently control each one, adjusting their output to compensate for any disturbances or to change the bubble's direction and speed. The separation distance between nacelles matters. Place them too close together and their warp fields interfere destructively, cancelling each other out. Space them too far apart and they can't combine effectively to create the transport effect. White's calculation showed that the optimal separation depends on the nacelle size and the desired warp speed. But the ratio matches what Star Trek's designers chose. Nacelles several times longer than they are wide, positioned at a distance equal to a few nacelle diameters, connected to a central hull by structural members that don't interfere with the warp fields. Even the pylons connecting the nacelles to the main hull in the Enterprise design serve a physical purpose. The structural connections need to be strong enough to hold everything together, but designed so they don't disrupt the warp field geometry. You can't just suspend the nacelles with cables. You need rigid structures that maintain precise positioning under the stresses of operation. The pylons in the Star Trek design sweep back at angles that minimize their cross-section relative to the warp field, which is exactly what physics suggests you should do. The twin nacelle configuration also creates natural redundancy. If one nacelle fails, you can theoretically continue operating with the other at reduced performance, perhaps dropping out of warp but maintaining some warp field effect to provide partial protection. In a single bubble design, any failure is catastrophic because the entire field collapses at once. White's analysis extended beyond just the nacelle placement to examine what shapes the nacelles themselves should have. Cylindrical or elongated structures proved more efficient than spheres or other geometries, again matching what Star Trek showed. The length to diameter ratio optimizes the amount of exotic energy needed versus the volume of space being warped. Longer, thinner nacelles require less total energy than shorter, fatter ones to achieve the same effect. The paper also addressed how matter entering or leaving the warp bubble would behave. If you're traveling through space at warp speed, you will encounter interstellar gas, dust, stray atoms, radiation, all the diffuse material that fills the supposedly empty void. This matter interacts with the warp bubble in complex ways, potentially causing drag or disrupting the field. The twin nacelle design creates a path through which matter can flow with minimal disruption, entering through the region between the nacelles and being deflected around the central hull. Science fiction had stumbled onto real physics through a combination of aesthetic intuition and narrative requirements. The writers wanted the Enterprise to feel powerful and purposeful, giving it engine pods that looked capable of tremendous thrust. The designers positioned those pods away from the main ship to emphasize their importance and create visual balance. The result happened to match what actual physics suggests is optimal for warp drive configuration. This wasn't the only example of science fiction accidentally predicting science fact. Robert Goddard's rockets from the 1920s strongly influenced science fiction writers, who then influenced engineers who built actual spacecraft decades later. The feedback loop between imagination and engineering has a long history, but the specificity of the Enterprise design, matching warp drive physics so closely, remains striking, suggesting that certain engineering solutions are so fundamental that they emerge independently whether you're working from physics equations or artistic vision. White's discovery that the Enterprise nacelle configuration was physically optimal didn't make building a warp drive any easier. All the problems remained: generating exotic energy, controlling the bubble, dealing with time dilation effects and causality violations, solving the horizon problem. But it gave researchers a concrete design target, showing that at least one aspect of the challenge had a clear answer. When someone eventually builds a faster-than-light spacecraft, it will probably look something like a Star Trek ship, not because of homage, but because physics constrains the possible configurations to a narrow range. While White was refining warp drive designs, other physicists were exploring an entirely different approach to faster-than-light travel: wormholes. Einstein and his colleague Nathan Rosen discovered wormholes mathematically in 1935 while studying black hole physics. Though they didn't call them wormholes at the time, the equations showed that a black hole's event horizon could theoretically connect to a white hole in another region of space-time, creating a bridge between distant locations. The problem was that this Einstein-Rosen bridge was unstable and non-traversable. It would collapse before anything could pass through from one side to the other. The concept languished as a mathematical curiosity for decades, until physicists Kip Thorne and Michael Morris revisited it in 1988, asking whether wormholes could be made traversable if you added the right kind of matter to hold them open. Their analysis showed that traversable wormholes were theoretically possible, but required the same exotic matter with negative energy that warp drives need. The requirements were actually worse than for warp drives because wormholes need negative energy throughout their entire throat, the tunnel connecting the two mouths, not just in a shell around a craft. A traversable wormhole would look nothing like the spinning vortexes beloved by science fiction films. From the outside, each mouth would resemble a spherical region of distorted space, perhaps looking like a lens or mirror depending on how light bends around it. Step through the mouth and you'd find yourself in a tunnel whose walls curve away from you, though the tunnel might be much shorter than the distance between the two mouths when measured through normal space. The two mouths could be separated by arbitrary distances in ordinary space, while being connected by a short path through the wormhole. Place one mouth near Earth and the other near Proxima Centauri, and you could walk from one star system to the other in minutes despite being 4 light-years apart. The wormhole creates a shortcut through space-time itself, folding the fabric of the universe so that distant locations become adjacent. This sounds suspiciously like warp drive, and indeed the physics are closely related. Both involve manipulating space-time geometry to achieve faster-than-light travel without locally exceeding light speed. The difference is that warp drives move a bubble through space, while wormholes create static connections between locations. You could think of a wormhole as a permanent warp tunnel that you travel through conventionally, rather than riding in a bubble that moves. For 50 years after Morris and Thorne's paper, wormholes remained firmly theoretical. Nobody had demonstrated that they could exist even in principle without exotic matter, and creating them seemed impossibly difficult. Then, in 2022, a team at Google and Caltech announced that they had observed wormhole dynamics using a quantum computer, creating the first experimental evidence that wormholes could be realized physically. The experiment used 9 qubits on Google's Sycamore quantum processor to simulate a simplified version of a gravitational system. The researchers programmed the quantum computer to evolve according to equations derived from the Sachdev-Yekitaev model, a theoretical framework that exhibits holographic duality between quantum mechanical systems and gravitational spacetimes. This duality, sometimes called the ER equals EPR conjecture, after Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement, suggests that quantum entanglement and wormholes are fundamentally the same phenomenon. When the researchers entangled 2 separate quantum systems and then performed specific operations on them, they observed behavior consistent with information traveling through a wormhole connecting the 2 systems. A qubit inserted into one system appeared to tunnel through and emerge from the other system with the characteristic time delays and signal properties that a traversable wormhole would produce. The experiment didn't create an actual wormhole that you could walk through, but it demonstrated that wormhole physics emerges naturally from quantum mechanical systems in the right configuration. The significance extends beyond merely observing wormhole-like behavior in a simulation. The holographic principle that underlies this work suggests that gravity and quantum mechanics are 2 descriptions of the same underlying reality. If quantum entanglement really is equivalent to wormholes, then wherever you have entanglement, which is everywhere in the quantum world, you have tiny wormholes connecting entangled particles. The fabric of space-time at the quantum scale might be riddled with these microscopic connections. Scaling up from quantum computers to macroscopic traversable wormholes remains a challenge with no clear solution. The quantum wormhole in the Google experiment was purely informational. Qubits aren't physical objects that you could transport through space. Creating a wormhole large enough and stable enough to send matter through would require exotic matter with negative energy, just as warp drives do, and probably in larger quantities given the need to fill the entire throat rather than just a shell. Juan Maldacena, Alexei Milikin, and Fedor Popov published work in 2020 showing that certain theoretical frameworks predict humanly traversable wormholes might exist without impossible energy requirements. Their analysis used the Randall-Sundrum model, a speculation about extra dimensions that tries to explain why gravity is so much weaker than the other fundamental forces. In this model, our universe is a 4-dimensional membrane floating in a higher dimensional space, and gravity can propagate through these extra dimensions while other forces remain confined to our membrane. The Randall-Sundrum framework allows for wormholes stabilized by ordinary fermions, particles like electrons and quarks that make up normal matter, rather than exotic matter with negative energy. The fermions create a Casimir-like effect similar to what Harold White discovered in his microscopic cavities, generating the negative energy needed to hold the wormhole open through quantum vacuum effects, rather than requiring exotic matter from some unknown source. These wormholes would still be technically challenging to create and maintain. You'd need to arrange matter with incredible precision, in higher dimensional configurations that we can't directly manipulate. The wormholes would be small, perhaps only a few meters across, and they would create dangerous radiation fields near their mouths. Travelers would experience intense tidal forces passing through the throat, though not so intense they couldn't survive. The traversal time would be very short from the traveler's perspective, but appear much longer to outside observers. The Randall-Sundrum wormholes also have strange properties regarding time dilation. Because of how the extra dimensions affect space-time curvature, a person entering the wormhole would experience enormous acceleration as they fell through the throat, gaining what physicists call a large boost factor. This acceleration would cause time dilation, meaning the traveller would age very little while centuries or millennia passed outside. The wormhole essentially functions as a time machine to the future, though not to the past. This creates obvious problems for two-way interstellar travel. You could send explorers through a wormhole to a distant star system, and they would arrive quickly from their perspective. But by the time they returned through the wormhole, everyone they knew would be long dead. The wormhole would be useful for one-way missions or for sending information and resources, but not for maintaining regular two-way contact between star systems. Research continues on finding ways to make traversable wormholes more practical. Some physicists explore whether microscopic wormholes, too small to send people through but large enough to send information, might be achievable with less extreme requirements. Others investigate whether wormholes could be made traversable in both time directions, allowing travelers to return to roughly the same era they left. Still others work on the theoretical foundations, trying to understand which frameworks in quantum gravity and string theory allow for traversable wormholes and which forbid them. The connection between wormholes and quantum entanglement offers perhaps the most promising avenue. If entanglement really does create tiny wormholes, then manipulating entanglement might let us enlarge those wormholes to macroscopic scales. This would require unprecedented control over quantum systems, maintaining entanglement among trillions of particles simultaneously, while enlarging the associated wormhole without it collapsing. Nobody knows if this is possible, but at least it provides a concrete physical mechanism to investigate, rather than just assuming exotic matter exists somewhere. Wormholes offer certain advantages over warp drives for interstellar travel. Once created, a wormhole requires no energy to use. You just travel through it conventionally. Multiple trips through the same wormhole become cheap compared to activating a warp drive for each journey. A network of wormholes connecting multiple star systems would enable rapid transit throughout the network without the energy costs of point-to-point warp travel. The disadvantages are equally significant. Creating wormholes probably requires more exotic matter or energy than warp drives, spread throughout the throat rather than concentrated in a shell. Wormholes are static structures that can't be moved easily, so you can only travel between whatever endpoints you've managed to construct. If something goes wrong with a wormhole while you're inside, the consequences could be catastrophic as the throat collapses on you. Warp drives at least keep you in control of your own journey. The question of whether wormholes or warp drives represents a better path to interstellar travel depends on factors we don't yet understand. Which requires less exotic matter, which is more stable and controllable, which can be constructed with available technology. These questions remain open as research on both approaches continues. Meanwhile, entirely different physics suggests another possible route to faster-than-light travel, one that emerges from the strange world of quantum mechanics. Quantum mechanics allows particles to do something impossible according to classical physics. They can tunnel through barriers that they shouldn't have enough energy to overcome. Fire an electron at a potential energy barrier, and even if the electron lacks sufficient energy to surmount the barrier classically, there's a probability it will appear on the other side, as if it had bored a tunnel through. This phenomenon, called quantum tunneling, is well established, and forms the basis for devices like scanning tunneling microscopes and flash memory. In 1962, physicist Thomas Hartmann published a calculation showing that quantum tunneling leads to a counterintuitive result. The time it takes for a particle to tunnel through a barrier hardly increases as you make the barrier thicker. Double the barrier width, and the tunneling time increases only slightly. Make the barrier thick enough and particles crossing it arrive faster than light could travel the same distance through empty space. This seems to violate special relativity, which forbids anything from exceeding the speed of light. The result is so shocking that many physicists initially refused to believe it, suspecting that Hartmann's calculation contained some subtle error. But decades of subsequent work confirmed the basic conclusion. Quantum tunneling exhibits what's now called the Hartmann effect. Tunneling time becomes independent of barrier thickness for sufficiently thick barriers, leading to apparent superluminal speeds. Recent experiments have made the situation even more puzzling. In 2020, researchers led by Ephraim Steinberg at the University of Toronto measured the tunneling time of rubidium atoms through a laser-induced barrier with unprecedented precision. Their measurements showed that the atoms spent very little time inside the barrier, far less than you would expect if they were travelling at light speed through the thickness of the barrier. Some interpretations of the data suggest the tunneling process is instantaneous, taking no time at all beyond what's required for the particle to reach and leave the barrier. Another group led by Igor Litvinyuk at Griffith University measured electron tunneling out of hydrogen atoms, finding that the process takes at most 1.8 attoseconds. An attosecond is 1/1000th of a billionth of a second, and 1.8 attoseconds is far too short for the electron to traverse the barrier thickness at light speed. Again, the tunneling appeared faster than light. These experiments forced physicists to confront what it means for a quantum particle to have a speed or a trajectory. Classical physics assumes objects have definite positions and velocities at every moment, but quantum mechanics rejects this picture. A quantum particle exists as a probability wave spread across space until you measure it, at which point it collapses to a specific location. The concept of how fast the particle was moving between measurements becomes slippery because the particle wasn't really moving along a path in the classical sense. The apparent faster-than-light motion in quantum tunneling comes from a measurement artifact. Before the barrier, you can measure the wave packet's center and define that as the particle's initial position. After the barrier, you measure where the particle appears and define that as its final position. If you divide the distance by the time that elapsed, you get an apparent speed that can exceed light speed. But this calculation assumes the particle followed a direct path at constant velocity, which isn't what actually happened. What really occurs is that the quantum wave packet hits the barrier and splits into two parts, a reflected portion that bounces back and a transmitted portion that tunnels through. The transmitted portion is a highly distorted version of the original wave packet, compressed and reshaped by the tunneling process. When you measure the particle on the far side, you're collapsing this distorted wave packet, and the measurement is more likely to find the particle near the leading edge of the wave than at its center. This means particles detected after tunneling were always part of the front edge of the probability wave that approached the barrier. They didn't travel faster than light, they were simply the subset of the wave packet that was already ahead when tunneling began. The confusion arises from comparing the wave packet's center before tunneling with the detected particle position after tunneling, which mixes two different probability distributions. Several physicists, including Steinberg himself, emphasize that no information travels faster than light in these experiments. You can't use quantum tunneling to send a message faster than light because you can't control which individual particles will tunnel versus which will be reflected. The tunneling probability is fixed by quantum mechanics and doesn't carry information. Even if particles arrive faster than you'd expect, you can't encode data in their arrival times in a way that would allow superluminal signaling. The situation is analogous to cutting a long rope such that the near end stays in your hand while the far end falls to the ground. The far end hits the ground very quickly, potentially faster than the propagation speed of waves along the rope, but this doesn't let you send information faster than wave speed because you can't control when the far end was already about to fall. The speed at which the end hits depends on the initial conditions, not on any information you're trying to transmit. Despite these clarifications, the quantum tunneling mystery persists. Recent proposals by physicists Patrick Schach and Enno Gieser at Darmstadt Technical University suggest new ways to measure tunneling time that might resolve some of the apparent paradoxes. They propose using the tunneling particle itself as a clock, comparing its internal quantum oscillations with those of a non-tunneling reference particle. Their calculations suggest that time might flow differently for tunneling particles than for particles travelling through empty space, though not in a way that allows faster-than-light signaling. The implications for faster-than-light travel are unclear. Quantum tunneling definitely cannot be used to transport macroscopic objects like spacecraft faster than light. The effect relies on quantum superposition and works only for individual particles or very small quantum systems. As objects get larger, quantum effects wash out and classical physics takes over, eliminating the possibility of tunneling. Some researchers speculate about whether quantum tunneling might enable faster-than-light communication at the particle level, even if not for transporting matter. If you could reliably tunnel particles between two locations and detect their arrival, might you create a superluminal telegraph? The problem is that quantum mechanics prohibits using tunneling this way because you can't control which particles tunnel or force them to carry meaningful information. Every scheme that tries to exploit tunneling for communication runs into the no communication theorem, a fundamental result of quantum mechanics that forbids faster-than-light information transfer. Still, the fact that quantum mechanics naturally produces superluminal effects, even if those effects can't be harnessed for practical faster-than-light travel, suggests that the speed of light isn't quite as absolute a barrier as it first appears. The prohibition is more subtle than simply, nothing can go faster than light. Rather, the rule is that you can't transmit information or energy faster than light in a way that would violate causality. Quantum effects that appear superluminal don't actually violate this rule when you analyse them carefully. Research into quantum tunnelling continues, driven partly by its applications in electronics and partly by the fundamental mystery it represents. Every new measurement technique reveals additional complexity, suggesting we still don't fully understand what happens during tunnelling. Whether these mysteries will eventually point towards some route to faster-than-light travel or simply deepen our understanding of quantum mechanics remains to be seen. The energy requirements for faster-than-light travel, whether through warp drives, wormholes, or some other method, remain the most significant practical barrier. Understanding just how much energy is needed and how those requirements have evolved over decades of research reveals why the challenge is so formidable. When Miguel Alcubierre first calculated the energy needed for his warp drive in 1994, the answer came out absurd: mass energy equivalent to several times the mass of Jupiter, concentrated into exotic matter and arranged in a thin shell around the spacecraft. To put this in perspective, Jupiter contains about 1.9 times 10 to the 27th power kilograms of matter. Converting all of that mass into energy, using Einstein's mass-energy equivalence, would yield about 1.7 times 10 to the 44th power joules, roughly the amount of energy the Sun produces in 100 million years. The prospect of harnessing energy on this scale was obviously hopeless. Even if humanity could somehow extract and control the entire mass energy of Jupiter, which is impossible with any foreseeable technology, we would still need to convert it into negative energy, which we don't know how to do at all. The calculation effectively closed the door on warp drives as anything but mathematical curiosities. Then physicists began optimizing. Harold White's 2012 calculations showed that reshaping the warp bubble from a sphere to a torus and oscillating the field intensity could reduce requirements dramatically. His refined model suggested that roughly 700 kilograms of exotic matter might suffice, a reduction of 25 orders of magnitude. 700 kilograms is still an enormous challenge, but it's at least conceivable that some future technology might handle masses in that range. The optimization came from understanding how efficiently you can warp space-time. Alcubierre's original spherical shell distributed the warp effect uniformly, which meant warping a large total volume of space. White's toroidal design concentrated the warp effect into a smaller volume, while achieving the same transport effect, and oscillating the field meant you only needed peak negative energy for brief moments, rather than sustaining it continuously. Further refinements pushed the requirements down even more. Researchers explored what's called the Van den Broek bubble, a modification where you nest warp bubbles inside each other like Russian dolls. The outer bubble has a tiny opening barely larger than an atom, but the interior expands to contain a comfortably sized spacecraft. This bizarre geometry dramatically reduces the total volume that needs to be warped, lowering energy requirements by many additional orders of magnitude. The nested bubble design creates its own problems. The tiny outer opening means anything entering or leaving the ship would experience enormous tidal forces as it squeezes through the mouth. The interior expansion might be unstable, collapsing catastrophically if disturbed. The control systems needed to maintain such a delicate configuration could prove impossible to engineer, but it demonstrates that clever geometric tricks can reduce energy requirements far below initial estimates. By 2024, some calculations suggested that a warp bubble 10 meters across might require only a few tons of exotic matter rather than hundreds of kilograms. This represents a reduction of something like 30 orders of magnitude from Alcubierre's original estimate. The energy requirements haven't disappeared, but they've become small enough that you could at least imagine future technologies handling them. The transition to positive energy warp drives changed the calculation entirely. The subluminal designs by Fuchs, Helmerich and others require ordinary mass energy rather than exotic matter, which seems like progress until you look at the numbers. Their calculations show that you need mass energy equivalent to several Jupiter masses after all, arranged in specific geometric configurations around the spacecraft. The energy requirements went back up by 25 orders of magnitude. Why would positive energy designs require more energy than negative energy ones? The answer lies in how efficiently different matter configurations can curve spacetime. Negative energy creates strong gravitational repulsion, pushing space apart with less total energy than positive energy can pull it together. When you're limited to positive energy, you need much larger quantities to achieve the same space-time distortion. This trade-off between exotic matter and energy requirements defines the current state of warp drive research. You can build a drive that needs relatively little energy, but requires matter we don't know how to create, or you can build one that uses ordinary matter but needs preposterous amounts of it. Neither approach is currently feasible, but at least both represent engineering challenges rather than fundamental physics barriers. The energy question also depends critically on how fast you want to go. A warp bubble travelling at 10% of light speed requires far less energy than one travelling at 10 times light speed. The energy scales roughly with the square of the velocity ratio, meaning that doubling your speed quadruples your energy needs. This creates a practical limit even if we solve the exotic matter problem. There's an energy threshold beyond which faster speeds become prohibitively expensive. Some researchers propose staged approaches. Build a modest warp drive first, one that operates at a fraction of light speed using achievable energy sources, even if it requires more exotic matter than we currently know how to produce. Once you have a working drive at low speeds, refine it to go faster as technology improves. This mirrors how rocket development proceeded, starting with small experimental vehicles before building moon rockets and interplanetary probes. The energy would come from somewhere in the spacecraft, probably some form of matter-antimatter reactor or exotic power source we haven't developed yet. Current nuclear reactors produce about 10 to the 9th power watts continuously, while spacecraft warp drives might need 10 to the 18th power watts or more, 9 orders of magnitude more powerful. Fusion reactors currently under development might reach 10 to the 12th power watts, still 6 orders of magnitude too weak. Antimatter offers the highest energy density possible. Converting 1 kilogram of matter plus 1 kilogram of antimatter into pure energy yields about 10 to the 17th power joules, enough to power a modest warp drive for a short time. The problem is producing and storing antimatter. Current particle accelerators create antimatter atoms at rates measured in nanograms per year, and storing antimatter requires magnetic traps that would fail catastrophically if the power supply ever flickered. Some speculative proposals suggest extracting energy directly from the quantum vacuum, essentially feeding the warp drive with the same Casimir effect energy that might provide the negative energy for the warp bubble. This seems elegant, closing the energy loop, but the amounts of vacuum energy we can extract are measured in microwatts, many orders of magnitude too small for warp drives. Scaling up vacuum energy extraction to useful levels might be impossible due to quantum field theory constraints. The energy question also affects how you accelerate and decelerate. You can't just turn on a warp drive instantly because the energy requirements are too high. You need to ramp up gradually. Similarly, when approaching your destination, you need to slow down carefully rather than turning off the drive and suddenly finding yourself traveling at many times light speed with no way to stop. The acceleration and deceleration phases might take longer than the cruise phase, limiting the drive's usefulness for short trips. Energy storage becomes critical. A spacecraft operating a warp drive can't easily refuel mid-journey, since the drive moves the entire bubble including any fuel you're carrying. You need to carry enough energy for the entire trip, including acceleration, cruise, and deceleration, plus emergency reserves. This might require fuel tanks larger than the spacecraft itself, creating engineering nightmares around mass distribution and structural integrity. Despite these challenges, the steady progress in reducing energy requirements from impossible to merely astronomical suggests that continued refinement might make warp drives feasible someday. Every factor of 10 reduction in energy needs brings the goal a step closer to technological capability, even if we're still many factors of 10 away from achievable levels. Meanwhile, scientists have begun thinking about how to detect warp drives if other civilizations have already built them. If intelligent civilizations elsewhere in the galaxy or beyond have developed warp drives before us, and if they're using those drives to explore space, we might be able to detect their activities through the gravitational waves their spacecraft produce. This prospect emerged in 2024 when physicist Katie Clough and her colleagues at Queen Mary University of London published research modelling what happens when a warp bubble fails catastrophically, simulating a warp core breach in Star Trek terminology. Clough's team used the same numerical relativity techniques that model black hole collisions and neutron star mergers, adapting those methods to simulate warp drive dynamics. They started with a stable warp bubble containing a small spacecraft, then abruptly removed the exotic matter sustaining the bubble, mimicking what would happen if the drive system failed. The equations showed that the bubble doesn't simply vanish, it collapses violently, radiating energy as gravitational waves and matter shells. The gravitational wave signature would be distinctive. Unlike black hole mergers, which produce a characteristic chirp pattern as the black holes spiral together before colliding, a warp bubble collapse would create a burst of gravitational radiation at specific frequencies determined by the bubble's size and collapse time. For a bubble 10 meters across collapsing over microseconds, the radiation peaks around 300 kHz, far above the frequencies that current detectors like LIGO can observe, but potentially detectable with future upgraded instruments. The amount of energy released depends on the warp bubble's speed and mass. A bubble travelling at 10% of light speed and containing a modest spacecraft releases enough energy during collapse that it would be detectable from a distance of up to 1 megaparsec, roughly 3.3 million light-years. This encompasses thousands of galaxies, meaning that if warp-capable civilizations exist in our cosmic neighbourhood and occasionally experience drive failures, we might eventually detect their accidents. Clough emphasized that her simulations assume specific warp bubble configurations and collapse scenarios. Different warp drive designs might produce different gravitational wave signatures, and the collapse might proceed differently depending on what caused the failure. But the basic prediction seems robust. Any warp bubble catastrophically failing releases a burst of gravitational radiation strong enough to potentially observe from interstellar distances. This creates an exciting prospect for the field of gravitational wave astronomy. Since the first detection of gravitational waves in 2015 from colliding black holes, detectors have catalogued dozens of events from various sources. Most are black hole mergers, but neutron star collisions and other exotic phenomena contribute to the growing database. Adding warp drive failures to the list of potential sources gives astronomers another target to search for in the gravitational wave data. The challenge is frequency. Current detectors operate at frequencies from tens to thousands of hertz, optimized for detecting black holes and neutron stars. Warp bubble collapses might produce radiation at hundreds of kilohertz or even megahertz frequencies, requiring entirely different detector designs. Some proposed space-based detectors could reach into these frequency ranges, but building them remains decades away. Even if we can't detect the gravitational waves directly, other signatures might reveal warp drive activity. A spacecraft operating a warp drive would accumulate high-energy particles on the bubble's leading edge, like bugs on a windshield but at cosmic velocities. When the drive shuts down, these particles get released in a burst of radiation that could be visible across interstellar distances. Looking for unusual transient bursts of high-energy photons or particles might reveal warp-capable spacecraft traveling through our region of space. The Breakthrough Listen initiative, funded by Yuri Milner's Breakthrough Initiatives and led by astronomers at the University of California, Berkeley, searches for technological signatures from extraterrestrial civilizations. While most of their effort focuses on radio signals and optical lasers, the program could expand to include searches for warp drive signatures once we understand better what to look for. Detecting a warp drive, even indirectly, would be among the most significant discoveries in human history, proving both that we're not alone and that faster-than-light travel is achievable. Conversely, if we never detect any evidence of warp drives despite searching carefully, that tells us something important too. It might mean that warp drives are common enough that civilizations use them routinely without major accidents, or it might mean that warp drives are so rare or difficult that no one has built them despite the universe being full of intelligent life. Or it might mean we're alone, the only technological civilization within detection range, in which case the question of faster-than-light travel becomes even more important for humanity's long-term survival and expansion. Some researchers suggested that unexplained high-energy astrophysical phenomena might already be warp drive signatures we haven't recognized yet. Fast radio bursts, intense pulses of radio emission lasting milliseconds that come from distant galaxies, remain poorly understood despite years of study. Most astronomers attribute them to natural sources like magnetars or colliding neutron stars, but could some fraction represent artificial sources like warp drives? The question of whether we would recognize alien technology when we saw it remains contentious. Our intuitions about what advanced technology looks like are shaped by our own engineering, but civilizations millions of years ahead of us might build things so different from our expectations that we would classify them as natural phenomena. A functioning warp drive might look to our instruments like an unusual gravitational lens, or a strange distortion in space-time that we attribute to dark matter or cosmic structure rather than recognizing it as artificial. These possibilities motivate building better detectors and developing more sophisticated analysis techniques. Future gravitational wave observatories will have higher sensitivity and broader frequency ranges, making them more likely to catch exotic signals we can't currently observe. Machine learning algorithms trained on simulated warp drive signatures might find patterns in existing data that human analysts missed. The search for technosignatures is becoming more sophisticated, incorporating lessons from decades of SETI research about where to look and how to avoid false positives. If we do detect an alien warp drive, the implications would be transformative. We'd know for certain that faster-than-light travel is possible because someone has done it. The detection would provide indirect evidence about how warp drives work. The gravitational wave signature would constrain models of warp bubble physics, potentially telling us whether exotic matter is required or whether positive energy approaches suffice. Every bit of information would help guide our own development efforts. The possibility that we might detect alien warp drives before building our own adds urgency to the search, but it also highlights how far we still have to go in understanding the physics well enough to engineer working drives. Despite decades of refinement and numerous breakthroughs in reducing energy requirements and finding alternatives to exotic matter, warp drives face profound challenges that no amount of engineering can easily solve. These aren't just technical problems, but fundamental issues rooted in how general relativity connects space, time, and causality. The horizon problem emerges from the structure of the warp bubble itself. When space contracts in front and expands behind at faster than light speeds, the interior of the bubble becomes causally disconnected from the exterior. Light rays or any other signal trying to travel from inside the bubble to outside can't cross the boundary because they would need to travel faster than light relative to local space-time. Similarly, signals from outside can't reach the interior. This creates an immediate control problem. If you're the pilot inside a warp bubble, you can't send commands forward to the bubble's leading edge to change its configuration, adjust its direction, or turn it off. Those commands would need to cross the causally disconnected boundary, which is forbidden by relativity. You're effectively trapped inside your own bubble, along for the ride but unable to steer. Some proposed solutions involve pre-programming the warp bubble before activation, setting up the entire trajectory in advance, so no mid-course corrections are needed. This works only if you know exactly where you're going and can navigate perfectly, accounting for every factor that might cause deviations. Given that you're traveling through space at many times light speed while unable to see what's ahead, the navigation requirements seem impossibly demanding. Other proposals suggest using quantum entanglement to communicate across the causally disconnected boundary. If you entangle particles on either side of the bubble wall before activating the drive, quantum correlations might persist despite the causal separation. But quantum mechanics forbids using entanglement to transmit classical information faster than light. The no communication theorem applies even here. You can't send steering commands through entanglement any more than you can send them through normal signals. A third approach involves designing warp bubbles that avoid creating absolute horizons, perhaps through clever manipulation of the warp field geometry. Some configurations might allow thin channels where information can still propagate between interior and exterior, though these channels would be unstable and might compromise the bubble's integrity. The trade-off between control and performance might force accepting lower speeds in exchange for retaining the ability to navigate. The time travel problem goes deeper. General relativity allows for closed time-like curves, paths through space-time that loop back to their own past. Whenever you have faster-than-light travel, you can potentially arrange two trips such that the ending point of the second trip is before the starting point of the first trip, relative to some reference frame, creating a time loop. This opens all the famous paradoxes: killing your grandfather before he meets your grandmother, preventing your own birth, creating contradictions that seem to break causality. Some physicists argue that quantum mechanics resolves these paradoxes through consistency protection. Any action that would create a contradiction gets suppressed by quantum effects. The probability of the grandfather killing event drops to exactly zero, even though classical physics would allow it. Others suggest that time travel simply isn't possible. Any attempt to create a closed, time-like curve would cause the spacetime configuration to become unstable and collapse before the loop closes. The chronology protection conjecture, proposed by Stephen Hawking, states that the laws of physics conspire to prevent time travel on macroscopic scales. Quantum effects that we can currently neglect might become important exactly when time travel would otherwise be possible, destroying the closed time-like curve before it forms. Warp bubbles trying to create time machines might experience quantum instabilities that tear them apart, making time travel impossible as a practical matter, even if the classical equations allow it. Stability issues plague all warp drive designs. Creating and maintaining extreme spacetime curvatures requires fine-tuned control over enormous energy densities. Any slight perturbation, stray particles entering the bubble, quantum vacuum fluctuations, or control system errors could destabilize the bubble. Once the bubble begins collapsing, the process might be irreversible and catastrophically violent. Simulations suggest that warp bubbles might be only marginally stable at best. Katie Clough's gravitational wave research showed that removing the exotic matter sustaining a bubble causes immediate collapse. Other studies found that particles or radiation entering the bubble from outside create disturbances that grow over time, eventually destroying the bubble. The timescales for these instabilities might be so short that warp bubbles can only exist for microseconds before collapsing. Navigation presents yet another challenge, even if you solve the horizon problem. At many times light speed, you have almost no time to react to obstacles. An asteroid in your path would be impossible to detect and avoid. You'd hit it before light from the asteroid could reach your sensors. Even if you could see ahead, changing course requires adjusting the warp bubble geometry, which might take longer than you have to react. Some designs propose using deflector shields, regions of intense gravitational or electromagnetic fields around the bubble that push obstacles out of the way before impact. But generating these fields might require additional exotic matter or energy beyond what the drive itself needs. The interaction between the deflector fields and the warp bubble might create instabilities. Every solution introduces new problems that need solving. Radiation hazards could make warp drives lethal to their crews. As the bubble moves through space, it accumulates particles and radiation on its leading edge. When the drive shuts down, all this accumulated energy gets released in a burst directed forward. The intensity might be enough to sterilize planets in the direction you're traveling, making warp-capable spacecraft existential threats to any civilizations in their path. Even inside a stable bubble, radiation effects might be problematic. Quantum field theory predicts that accelerating through a vacuum creates a bath of thermal radiation called Unruh radiation, analogous to Hawking radiation near black holes. For a warp bubble, the effective acceleration could be enormous even though you're not accelerating locally, potentially exposing the crew to lethal doses of high-energy particles. These challenges explain why, despite genuine progress in warp drive physics over the past 3 decades, no one seriously expects to build a working drive anytime soon. We've moved the goalposts from impossible to incredibly difficult, but incredibly difficult still means beyond anything current technology can achieve, and possibly beyond anything future technology will achieve. The question is whether continued research will reveal solutions to these problems, or whether some of them represent fundamental limits that no amount of cleverness can overcome. The horizon problem might have no solution consistent with relativity, meaning warp drives that exceed light speed will always be uncontrollable. Time travel paradoxes might indicate that faster than light travel is genuinely forbidden by physics we don't yet understand. Or perhaps these problems have solutions we simply haven't thought of yet. The history of physics includes many examples of obstacles that seemed insurmountable until someone found a clever workaround. The challenge is distinguishing between difficult problems that will eventually yield to ingenuity and impossible problems that reflect deep prohibitions in the laws of nature. What's certain is that anyone claiming warp drives are imminent, or that faster than light travel is just around the corner, is either mistaken or misrepresenting the state of the field. Serious researchers emphasize that we're still at the stage of understanding basic physics, analogous to where aeronautics was in the 19th century before the Wright brothers flew. We've established that warp drives might be possible in principle, which is progress, but turning that possibility into reality could take centuries. The quest to understand warp drives has generated insights that extend far beyond spacecraft propulsion. The mathematical tools and physical principles developed for analyzing exotic spacetime geometries apply to numerous other areas of physics, from cosmology to quantum field theory to condensed matter physics. Even if warp drives never become practical, the intellectual journey has value. Gravitational wave astronomy benefits directly from warp drive research. The numerical techniques scientists developed to simulate warp bubble dynamics are nearly identical to those used for modelling black hole mergers and neutron star collisions. Katie Clough's team adapted black hole simulation codes to study warp bubble collapse, and those adaptations flow both directions. Improvements in warp drive modelling enhance our ability to predict gravitational wave signatures from other exotic sources. The connection works because both problems involve solving Einstein's field equations for highly dynamic, strongly curved spacetimes. Whether you're tracking two black holes spiraling together or a warp bubble forming and collapsing, you need powerful computers running sophisticated codes that integrate the equations forward in time. The expertise developed in one domain transfers directly to the other. Cosmology gains from understanding how spacetime behaves when pushed to extreme conditions. The early universe, particularly during the inflationary epoch immediately after the Big Bang, experienced rapid expansion that shares mathematical similarities with warp drive physics. Some inflationary models even use metrics that look similar to Alcubierre's warp bubble, with space expanding explosively in certain regions while remaining flat elsewhere. Studying warp drives helps cosmologists understand what happens when spacetime expansion becomes extreme. Can quantum effects stabilize or destabilize the expansion? How do particles and fields behave in rapidly expanding regions? What observational signatures would different expansion scenarios produce? Answers to these questions inform models of cosmic inflation and help distinguish between competing theories about the universe's first moments. Metamaterials research intersects with warp drive physics in unexpected ways. Scientists exploring negative index metamaterials, which bend light in unusual directions, discovered that the mathematical description of light propagating through these materials closely resembles light propagating through warped spacetime. You can create optical analog warp drives where light appears to move faster than its vacuum speed when travelling through carefully engineered materials. These optical analogs don't violate relativity because the light isn't actually exceeding its maximum speed. The material's structure creates an effective geometry that mimics warped spacetime for electromagnetic waves. But studying these analogs provides insights into how warp drives would behave without needing to actually warp spacetime. Researchers can test control strategies, measure how pulses propagate through the warped region, and explore stability issues using tabletop experiments instead of requiring exotic matter and enormous energies. Quantum field theory in curved spacetime receives significant attention from warp drive researchers. The Casimir effect that Harold White studied represents just one example of how quantum fields behave differently when spacetime isn't flat. Understanding these effects completely requires developing better mathematical tools for handling quantum mechanics in arbitrary curved spacetimes, tools that have applications throughout fundamental physics. The Unruh effect, where accelerating observers detect thermal radiation that inertial observers don't see, becomes relevant for warp drives because passengers in a warp bubble might experience effective acceleration even though they're locally at rest. Calculating the Unruh radiation inside a warp bubble requires sophisticated quantum field theory that pushes the boundaries of current understanding. These calculations improve our general understanding of how quantum fields and gravity interact. Black hole physics connects to warp drives through the shared mathematics of horizons and causality. The event horizon around a black hole creates a causal boundary similar to the horizon problem in warp bubbles. Information that crosses a black hole's event horizon cannot return to the outside universe, just as information inside a warp bubble cannot escape to external space. Studying one type of horizon illuminates the other. Hawking radiation, the quantum mechanical process by which black holes slowly evaporate, might have analogues in warp bubble physics. The transition region where a warp bubble forms or collapses could generate particle creation through similar quantum effects. Understanding these processes helps physicists model black hole evaporation more accurately, and might even provide clues about how to detect small black holes created in particle accelerators or floating in space. Energy extraction from vacuum fluctuations, even if it never powers warp drives, could revolutionize electronics and power generation at small scales. White's work on Casimir cavities was originally funded to explore energy harvesting, and that application remains potentially valuable. Imagine sensors or medical implants that never need battery replacement because they draw power continuously from quantum vacuum fluctuations. The energy available is tiny, measured in microwatts, but for certain applications that's sufficient. The engineering challenges mirror those of early transistors and integrated circuits. The first transistors generated only tiny amounts of power and couldn't do much individually, but connecting millions of them on a single chip created the computer revolution. Similarly, individual Casimir cavities produce minuscule energy, but arrays containing millions or billions of cavities could generate useful power. The fabrication techniques needed to build such arrays would advance nanotechnology and micromanufacturing generally. Materials science benefits from understanding how matter behaves under extreme spacetime curvatures. While we can't create strong gravitational fields in laboratories, we can calculate how materials would respond theoretically. And those calculations reveal fundamental properties of how atoms and electrons interact. Some researchers explore whether exotic electronic properties emerge in materials experiencing simulated curved spacetime through acoustic or electromagnetic analogues. Topological materials, which exhibit unusual electronic properties due to their mathematical structure rather than their chemical composition, show interesting connections to curved spacetime physics. The mathematical tools for describing topological phases sometimes resemble those used in general relativity, and insights from one field occasionally transfer to the other. Warp drive researchers studying exotic geometries might stumble onto new topological phases that materials scientists can then realize in actual materials. Quantum computing sees potential applications from wormhole physics research. The 2022 Google quantum computer experiment that observed wormhole-like dynamics demonstrated that quantum computers can simulate gravitational systems. As quantum computers become more powerful, they might be able to simulate warp drives and other exotic spacetimes with enough fidelity to test predictions that would be impossible to verify through actual experiments. These quantum simulations could accelerate warp drive research by allowing researchers to explore thousands of different geometries and configurations virtually, identifying promising designs before investing in expensive physical experiments. The simulations might also reveal unexpected instabilities or failure modes that analytical calculations miss, helping engineers avoid dangerous configurations if warp drives ever transition from theory to practice. Fundamental physics could be transformed by insights from warp drive research. Some physicists speculate that the difficulty of creating macroscopic negative energy might indicate something deep about the structure of spacetime and quantum mechanics. Perhaps the laws of physics incorporate built-in protections against causal paradoxes, with quantum effects automatically suppressing any configuration that would allow time travel. Understanding these protections could reveal new principles governing how quantum mechanics and gravity fit together. The cosmological constant problem, one of the biggest unsolved mysteries in physics, asks why the vacuum energy density is so much smaller than quantum field theory predicts. Calculations suggest the vacuum energy should be enormous, perhaps 10 to the 120 power times larger than observed. Yet the measured value is tiny, and we don't understand why. Studying negative energy and vacuum energy manipulation might provide clues about how this enormous discrepancy gets resolved. String theory and other quantum gravity theories benefit from concrete problems like warp drives that require understanding how quantum mechanics and gravity interact. Most work in these theories remains highly abstract, exploring mathematical structures without clear connections to observable phenomena. Warp drives provide specific scenarios where quantum gravity effects might become important, giving theorists concrete targets to aim for when developing predictions. The holographic principle, suggesting that all information in a volume of space can be encoded on its boundary, emerged partly from studying black hole physics. Wormhole research extending these ideas shows that similar holographic relationships connect entangled quantum systems across space. Warp drives and wormholes might eventually illuminate deep connections between quantum information, spacetime geometry, and the ultimate nature of reality. Education and public engagement gain from warp drive research by providing compelling examples of cutting-edge physics that capture public imagination. Students are more likely to pursue physics and engineering if they see scientists working on fantastic-sounding projects rather than incremental refinements of established knowledge. The aspirational quality of warp drive research Its connection to space exploration and science fiction makes it an effective gateway for introducing fundamental physics concepts. The cultural impact should not be underestimated. Humans have always been explorers, and the apparent impossibility of interstellar travel creates psychological barriers to thinking seriously about humanity's long-term future beyond Earth. Warp drive research, even if it never succeeds practically, maintains the dream that the stars are reachable. That dream motivates not just researchers working on warp drives, but engineers developing more conventional space technologies and educators training the next generation. International cooperation benefits from shared aspirational goals like developing warp drives. No single nation has resources sufficient to tackle such ambitious projects alone. Successful warp drive development, if it ever happens, will require coordinated efforts across decades or centuries by researchers from many countries working together. The collaborative infrastructure built around warp drive research strengthens scientific cooperation generally, creating networks and relationships that facilitate progress across many fields. These broader applications justify continued warp drive research. Even skeptics doubt spacecraft applications will ever materialize. The journey often matters more than the destination, and the intellectual journey toward understanding exotic space-time geometries and quantum vacuum effects generates value independent of whether anyone ever travels faster than light. Science advances through exploration of ideas, some of which succeed while others illuminate why certain things can't be done, and both outcomes advance human knowledge. While warp drives and wormholes capture most attention in faster-than-light research, physicists have explored numerous alternative approaches that might circumvent the speed limit through different mechanisms. These alternatives range from modestly speculative extensions of known physics to highly theoretical concepts that require entire new frameworks of understanding. Each offers unique advantages and faces its own set of challenges. String theory, the leading candidate for a theory of quantum gravity, suggests that the universe contains more than the 3 spatial dimensions and 1 time dimension we experience directly. According to string theory, there are 6 or 7 additional spatial dimensions curled up at incredibly small scales, perhaps at the Planck length of about 10 to the negative 35 meters. These extra dimensions are so tiny that we can't detect them with current technology, but their existence would dramatically change how physics works at fundamental scales. Gerald Cleaver and Richard Abusi from Baylor University proposed in the late 2000s that manipulating these extra dimensions might enable faster-than-light travel without requiring exotic matter. Their idea involves expanding one of the extra dimensions preferentially in the direction you want to travel, while contracting it in the opposite direction. This dimensional manipulation would create a pressure gradient in the dark energy that fills space, pushing your spacecraft forward at speeds exceeding light without violating relativity in the usual 3 spatial dimensions. The concept builds on observations that dark energy, the mysterious component causing the universe's expansion to accelerate, seems connected to the vacuum energy of space itself. If the extra dimensions influence dark energy's properties, then changing the dimension's sizes might let you control dark energy locally. Creating a region where dark energy pushes strongly behind your spacecraft while pulling weakly ahead would accelerate you forward, potentially to arbitrary speeds. The energy requirements for dimensional manipulation remain entirely theoretical and might be comparable to those for traditional warp drives. You would need to change the size of dimensions over macroscopic distances rather than just at a point, which probably requires enormous energy densities sustained over large volumes. The mechanism for actually manipulating dimensions is completely unknown. We have no experimental access to extra dimensions and no technology that could affect them, even if we understood how. Nevertheless, the approach offers potential advantages. It might avoid the negative energy requirement that plagues Alcubierre-style warp drives, instead using positive energy dark energy that already fills space. It might not create causally disconnected horizons, potentially allowing better control and navigation. The exotic matter needed might be less extreme than what standard warp drives require, though less extreme could still mean completely impossible with foreseeable technology. Testing dimensional manipulation theories faces obvious challenges. If extra dimensions exist and are accessible, detecting them requires energies far beyond what particle accelerators can currently produce. The Large Hadron Collider, the most powerful accelerator ever built, reaches energies of about 14 trillion electron volts. Impressive by human standards, but still about 16 orders of magnitude below the Planck scale, where extra dimensions become directly relevant. Future accelerators might narrow this gap, but probably won't close it completely. Some string theory variants predict large extra dimensions, bigger than the Planck scale and potentially accessible at lower energies. These scenarios remain highly speculative, but would make dimensional manipulation more feasible if they're correct. Researchers search for signatures of large extra dimensions in particle physics experiments, gravitational wave detections, and cosmological observations, but so far no convincing evidence has appeared. Modified gravity theories offer another alternative route to faster-than-light travel. These theories propose that Einstein's general relativity, while extremely accurate under normal conditions, breaks down or requires modifications in extreme situations. The modifications might involve additional fields that couple to matter, changes to how gravity propagates at large distances, or corrections that become important when spacetime curvature gets very large. Some modified gravity theories naturally predict phenomena resembling warp drives without requiring exotic matter. If gravity works differently at large scales or in high curvature regions, then configurations that seem impossible in standard general relativity might become achievable. The challenge is that most modified gravity theories were developed to explain cosmological observations like dark energy or galaxy rotation curves, not to enable faster-than-light travel, so whether they help with warp drives is unclear. Modified Newtonian dynamics, or MOND, changes how gravity behaves when accelerations become very small, much less than what we experience on Earth's surface. This modification was proposed to explain why galaxies rotate faster than visible matter can account for, potentially eliminating the need for dark matter. MOND doesn't directly address faster-than-light travel, but some researchers speculate that if gravity changes at low accelerations, it might also behave differently in other extreme regimes relevant to warp drives. The difficulty is that most modified gravity theories struggle to explain all observations successfully. General relativity works extraordinarily well across enormous ranges of scales and conditions, from laboratory experiments to solar system tests to cosmological observations spanning billions of light years. Any modification must reproduce all of general relativity's successes, while also explaining whatever new phenomena motivated the modification. Most attempts fall short somewhere, making them suspect as foundations for practical warp drive development. Tachyons, hypothetical particles that always travel faster than light, offer a completely different approach to faster-than-light travel. Special relativity doesn't forbid particles that never slow down to light speed, only particles that accelerate from below light speed to above it. A tachyon would have imaginary mass, meaning its mass squared is negative, which allows it to travel faster than light without violating energy conservation. If tachyons exist and we could interact with them, we might be able to use them for faster-than-light communication or travel. The problem is that tachyons create severe causality violations, even more blatant than those from warp drives. Because they travel faster than light, tachyons can be used to send signals backward in time relative to some observers, creating paradoxes. Most physicists believe tachyons don't exist precisely because they would allow causality violations, and whatever fundamental principles govern physics seem to forbid such violations. No experiment has ever detected a tachyon despite numerous searches over decades. Additionally, quantum field theories with tachyons turn out to be unstable. The vacuum state in such theories is not actually the lowest energy state, so the universe would spontaneously decay into some other configuration. This instability suggests that tachyons aren't physically realizable particles, but instead represent mathematical artifacts indicating that a theory has been formulated incorrectly. When physicists identify tachyons in a quantum field theory, they usually interpret this as a signal that they need to reformulate the theory, rather than as a prediction that faster-than-light particles exist. Quantum teleportation, despite its name, doesn't enable faster-than-light travel or communication, but does involve transferring quantum states across space in interesting ways. When two particles are entangled, measuring one particle instantaneously affects the other, regardless of the distance between them. This spooky action at a distance, as Einstein called it, seems to violate locality but actually doesn't allow transmitting information faster than light. The process works by destroying the quantum state of a particle at one location while recreating it at another location where an entangled partner exists. The recreation requires sending classical information about the measurement result at light speed or slower, so the overall process never transmits information faster than light. Nevertheless, some researchers explore whether quantum teleportation might be adapted for transporting matter, or whether similar quantum effects might enable faster-than-light phenomena under conditions we haven't yet explored. The ER equals EPR conjecture, mentioned earlier in connection with wormholes, suggests that quantum entanglement and wormholes are fundamentally the same thing. If this conjecture is correct, then whenever you have entangled particles, you have a microscopic wormhole connecting them through a higher dimensional space. Manipulating entanglement might let you enlarge these quantum wormholes to macroscopic size, creating traversable shortcuts through space. This approach remains highly speculative because we don't understand the connection between quantum mechanics and gravity well enough to say definitively whether ER equals EPR is correct. It's an elegant idea that unifies two seemingly unrelated phenomena, but elegant ideas don't always correspond to physical reality. Testing the conjecture requires observations that probe quantum gravity, which current experiments cannot do with sufficient precision. Vacuum engineering proposes that by manipulating the structure of space itself at quantum scales, we might be able to create unusual propagation properties for particles and fields. The quantum vacuum isn't truly empty but seethes with virtual particles and fields fluctuating according to quantum mechanics. If we could engineer the vacuum structure, perhaps through intense electromagnetic fields or other means, we might create regions where light propagates differently, or where particles can move faster than light in the modified vacuum. Some experiments have claimed to observe faster than light propagation through specially prepared materials, though these results remain controversial. Light travelling through materials with unusual refractive properties can appear to arrive before it would have if travelling through vacuum, but careful analysis usually shows that no information actually travels faster than light in vacuum. The light might travel faster than light travels in the material, but that's allowed because light slows down in materials. Creating a vacuum with modified properties on macroscopic scales would require energy densities and field strengths far beyond anything achievable with current technology. You might need electromagnetic fields trillions of times stronger than those in the most powerful lasers we've built, sustained over cubic meters rather than focused into microscopic spots. The engineering challenges seem insurmountable with foreseeable technology, though perhaps future advances in materials and energy systems will make such things possible. Warp drives using only positive energy, like the Bobrick-Martyr subluminal designs and the Fuchs-Helmerich improvements, represent another alternative that avoids the exotic matter problem entirely. While these don't enable faster-than-light travel in the original formulations, ongoing research explores whether positive energy designs might be extended to superluminal speeds through different space-time topologies or additional assumptions about matter properties. The advantage of positive energy approaches is that they only require matter and energy types that definitely exist, even if assembling the required amounts remains incredibly difficult. You don't need to discover new physics or create exotic matter, you just need very advanced engineering. This makes positive energy warp drives more plausible long-term prospects, even if they're not achievable in the near future. Hyperfast sublight travel, while not truly faster than light, might be good enough for practical interstellar travel. If you could accelerate a spacecraft to 99.99% of light speed, relativistic time dilation would make the journey appear much shorter to the crew than to observers back on Earth. A trip to a star 10 light-years away would take only about 4 months of subjective time for the crew, though more than 10 years would pass on Earth. The energy requirements for relativistic rockets are enormous, but don't require exotic physics. You just need extremely efficient engines and vast amounts of fuel. Antimatter rockets could theoretically achieve such speeds if we could produce and store antimatter in kilogram quantities, which is currently impossible, but might become feasible with future technology. Fusion rockets using deuterium and tritium might reach significant fractions of light speed if we can solve the engineering challenges of sustained fusion and effective propulsion. The disadvantage is that even at 99.99% of light speed crossing the galaxy would still take over 100,000 years of Earth time. The crew would experience only a few decades due to time dilation, but they could never return to the era they left. Everyone they knew would be dead, civilizations would rise and fall, and they would be traveling one direction into the future with no way back. For exploration this might be acceptable, For maintaining interstellar civilization, it's probably inadequate. Each of these alternative approaches faces its own challenges and uncertainties. String theory remains unverified experimentally. Modified gravity theories struggle to match observations. Tachyons probably don't exist. Quantum teleportation can't transmit information faster than light. Vacuum engineering requires impossible energies, and relativistic rockets don't actually exceed light speed. Yet each represents a legitimate avenue for research that might eventually reveal unexpected routes to interstellar travel. The diversity of approaches is actually encouraging. It suggests that multiple paths might lead to the same goal, increasing the probability that at least one will eventually succeed. Research on one approach often generates insights applicable to others, creating a network of mutually reinforcing investigations. Even negative results that rule out certain approaches are valuable because they narrow the search space and guide future efforts toward more promising directions. Harold White likes to compare warp drive development to the construction of Europe's great cathedrals, projects that took multiple generations to complete. The architects who laid the foundations knew they wouldn't live to see the finished building, but they worked anyway, contributing their part to something larger than themselves. The masons who carved stones for the upper levels were continuing work begun by their great-grandparents, carrying forward a vision that would be realized only by their great-grandchildren. Warp drive research has entered this phase. The current generation of physicists is laying foundations, developing the theoretical frameworks, refining the mathematics, identifying the challenges that will need solving. They're teaching students who will carry the work forward, who will teach their own students, passing knowledge and ambition across the decades or centuries until someone finally achieves the breakthrough that makes it all possible. Miguel Alcubierre, who started everything with his 1994 paper, didn't expect to live to see warp drives become real. He views his contribution as opening a door for others to walk through, demonstrating that the mathematics works even if the engineering remains centuries away. Harold White, who has spent the past 2 decades optimizing those equations and searching for experimental evidence, speaks openly about how he's building infrastructure for scientists who aren't yet born. The research continues regardless. Universities teach courses on advanced propulsion and metric engineering, introducing students to the physics of warp drives and wormholes, alongside more conventional topics. Conferences bring together researchers working on different aspects of the problem, sharing insights and collaborating across institutions and national boundaries. Private organisations like Applied Physics fund exploratory work that government agencies can't or won't support. The tools are improving. Warp Factory, the open-source software developed by Fuchs and Helmerich, lets anyone with the right mathematical background explore warp drive geometries and test new ideas. Gravitational wave detectors are becoming more sensitive, potentially capable of detecting evidence of alien warp drives if they exist. Quantum computers are revealing unexpected connections between quantum mechanics and gravitational physics, suggesting new approaches to old problems. The energy requirements continue dropping as researchers discover more efficient geometries and better ways to manipulate space-time. What started as needing all the mass energy of Jupiter has dropped to tons or kilograms in optimized configurations, and might drop further as understanding deepens. The transition from exotic matter to positive energy designs, while requiring more energy in current models, eliminates the single biggest physical obstacle. Breakthroughs happen unexpectedly. Nobody predicted that studying Casimir cavities would reveal nanoscale warp bubble structures. Nobody expected the optimal warp drive configuration to match Star Trek's Enterprise. Nobody anticipated that quantum computers would observe wormhole dynamics decades before anyone could build macroscopic wormholes. Each surprise suggests that the physics still has secrets to reveal, connections we haven't noticed, possibilities we haven't explored. The timeline remains uncertain. Optimists suggest that if research funding increases and talented physicists dedicate their careers to the problem, working prototypes might emerge within a century or two. Pessimists note that every advance reveals new complications, suggesting that warp drives might be forever just beyond reach, asymptotically approaching feasibility but never quite arriving. Realists acknowledge that we don't know enough to make predictions. The timeline could be short or could be infinite. What has changed decisively is the conversation. Faster-than-light travel is no longer dismissed as impossible fantasy. It's studied as tremendously difficult engineering, which means the questions have shifted from Could anyone ever do this? To what would it take to actually do this, and how do we get there? That transformation represents genuine progress, even if no spacecraft has warped anywhere yet. The implications ripple through everything humanity thinks about its future. If we remain confined to subliminal speeds, the galaxy stays forever vast and mostly inaccessible. A civilization expanding at a few percent of light speed, which would be revolutionary compared to current capabilities, would take millions of years to spread across the Milky Way. By the time humanity reached the far side of the galaxy, we would have diverged into hundreds of separate species barely recognizable as related. But if warp drives become real, the galaxy shrinks. Stars that seemed impossibly distant become potentially reachable within a human lifetime. Interstellar travel transitions from generational ship scenarios, where your descendants might arrive at the destination, to something more like the age of exploration, where sailors expected to return home after voyages to distant lands. Civilizations could maintain contact across interstellar distances, creating a galactic community rather than isolated pockets of humanity spreading into the dark. The search for extraterrestrial intelligence takes on new dimensions. If intelligent civilizations are common but constrained to subliminal speeds, they would be isolated from each other, making the universe seem empty even if it's full of life. If warp drives are possible, and some civilizations have built them, we might eventually detect their activity or even encounter their spacecraft exploring our corner of the galaxy. Every year we don't find evidence of other warp-capable species narrows the possibilities about how common faster-than-light travel might be. For now, the work continues. Researchers explore new warp bubble geometries, searching for configurations that reduce energy requirements or eliminate the need for exotic matter. Engineers develop better metamaterials that might eventually scale up to produce macroscopic negative energy. Quantum physicists study entanglement and holographic duality, looking for insights into how space-time emerges from quantum mechanics. Mathematicians refine the equations, ensuring that proposed solutions don't violate subtle consistency requirements. Students enter the field, drawn by the prospect of working on humanity's most ambitious engineering challenge. Some will spend their careers making incremental progress, contributing pieces that later generations will assemble into working systems. Others might make the crucial breakthroughs that suddenly make everything click into place, solving problems that stumped everyone before them. Most will move on to other areas after a few years, but even brief contributions add to the accumulated knowledge. The public follows with mixed interest. Science fiction keeps warp drives in the cultural consciousness, ensuring that each new development gets covered in popular media. Space enthusiasts celebrate every advance, treating minor theoretical refinements as steps toward an inevitable future. Skeptics dismiss the whole enterprise as wasted effort, arguing that resources should go towards solving problems we know how to solve rather than chasing dreams that might never materialize. But the cathedral grows regardless of whether any individual stonemason thinks the finished building will be beautiful. The work has value independent of whether it succeeds on any particular timeline. Understanding how space-time can be manipulated deepens our knowledge of general relativity and quantum mechanics. Techniques developed for modeling warp drives find applications in astrophysics and cosmology. The challenge pushes technology forward, creating tools and capabilities that prove useful for purposes nobody anticipated. If humanity does eventually build a warp drive and send spacecraft to other stars, the architects of that achievement will owe their success to Miguel Alcubierre's 1994 insight. Harold White's decades of optimization, the applied physics team's elimination of exotic matter, and countless other contributions from researchers whose names won't appear in the history books, but whose work was nonetheless essential. And if we never build a warp drive, if the remaining obstacles prove insurmountable and faster-than-light travel stays forever in the realm of fiction, the effort will still have been worthwhile. We will have learned exactly where the boundaries lie, which will be knowledge of its own kind. We will have developed new mathematics, new physics, new understanding of how the universe works at its most fundamental level, and we will have maintained the spirit of exploration that defines humanity at its best, refusing to accept limitations until we've exhausted every possibility. The universe waits. Stars beckon from across light years of void, promising wonders and discoveries beyond anything we can currently imagine. Whether we reach them quickly through warp drives or slowly through subliminal expansion, or never at all because the distances prove impassable, the question matters. It's worth asking, worth investigating, worth generations of effort to answer. Faster than light travel moved from impossible to improbable when nobody was paying attention. The next step from improbable to merely difficult might happen tomorrow or might never happen at all. But the work continues, the cathedral grows, and humanity keeps pushing against the boundaries of what physics allows. That persistence, that refusal to accept that we're confined to crawling across the cosmos at subluminal speeds, might be the most human trait we possess. The speed of light is fast by any ordinary standard, travelling roughly 186,000 miles every second. But the universe is incomprehensibly vast, with distances measured not in millions or billions of miles, but in light years and megaparsecs. At the speed of light, crossing our galaxy takes 100,000 years. Reaching other galaxies requires millions or billions of years. The universe is structured as if designed to keep civilizations isolated, forever alone on their cosmic islands, unless warp drives work, unless we can fold space, tunnel through it, or manipulate it in ways that let us sidestep that speed limit. Unless the apparent impossibility is just another barrier waiting for clever minds to find the loophole. That's what this generation is working on. The cathedral takes shape, stone by stone, equation by equation, experiment by experiment. When it's finished, if it's ever finished, humanity will step through to whatever waits beyond. And it all started with a young physicist watching Star Trek on a Friday night, wondering if maybe the math could actually work. The answer, it turns out, is yes, the math works. Now we just need to turn the math into reality, which might take a century or might take forever. But for the first time in human history, we know it's possible. That changes everything. If you enjoyed this journey through the cutting edge of physics and the dream of interstellar travel, hit that like button and subscribe to the channel. The universe is revealing its secrets one equation at a time, and we'll be here to explore each new discovery as it happens. Until next time, keep looking up.